There are places in the universe so vast, so filled with enigma, they defy our wildest imagination. Imagine a cosmic dance, a swirling vortex of stars, gas, and dust, where the familiar rules of physics seem to bend and twist in ways we're only just beginning to understand. This celestial ballet is happening right now, millions of light years away, in a galaxy that's become a focal point for astronomers seeking answers to some of the universe's most perplexing questions. We're talking about the Whirlpool Galaxy, officially known as M51, a breathtaking spiral galaxy that's a popular subject for astronomers and armchair stargazers alike. From here on Earth, even through a small telescope, it appears as a stunning swirl of light, its grand design captivating anyone who gazes upon it. But beyond its breathtaking beauty lies a cosmic playground of the bizarre, a place where strange phenomena occur with a frequency that borders on the unbelievable. It's a galaxy that challenges our assumptions about how galaxies form, evolve, and interact, pushing the boundaries of our current scientific understanding. For decades, scientists have been studying the Whirlpool Galaxy, using increasingly powerful telescopes to peer into its heart and unravel its secrets. And with every new observation, every new piece of data, they uncover something even stranger, something that adds another layer to the galaxy's already complex narrative. It's a galaxy in the throes of a dramatic interaction with its smaller companion galaxy, NGC 5195, a gravitational tug-of-war that's shaping both galaxies in profound ways. This interaction is not just a passive dance, it's a violent collision in slow motion, triggering intense bursts of star formation, distorting the galaxy's shapes, and likely driving the formation of some of the most extreme objects in the cosmos. It's a dynamic environment where black holes feast, neutron stars spin at incredible speeds, and mysterious signals emanate from unexpected places. The Whirlpool Galaxy is a living, breathing cosmic laboratory, constantly evolving and revealing new surprises to those patient enough to observe and interpret its complex language. It's a place where the extraordinary is the norm, and where every new discovery seems to raise even more questions than it answers. We've combed through countless scientific papers, analyzed data from the Hubble Space Telescope, the Chandra X-ray Observatory, and many others to bring you a journey into the heart of this cosmic enigma. We're going to explore 30 of the strangest phenomena observed in the Whirlpool Galaxy, each one stranger than the last. From supermassive black holes ripping apart stars to bizarre X-ray sources that defy conventional explanation, we'll delve into the anomalies that make this galaxy so fascinating and so mysterious. Get ready to question everything you thought you knew about galaxies and the universe they inhabit. This isn't just a list of facts, it's an invitation to explore the frontiers of astronomical discovery, to marvel at the sheer strangeness of the cosmos and to ponder our place within it. We'll uncover evidence of cosmic events so powerful they beg a belief, observe the birth and death of stars on a grand scale, and encounter objects so dense they warp the very fabric of space-time. Prepare to be amazed, bewildered, and perhaps a little bit humbled by the incredible power and mystery contained within the Whirlpool Galaxy, a true wonder of the universe that continues to challenge and inspire us. Join us as we count down 30 of the most bizarre and captivating phenomena that make M51 a truly extraordinary corner of the cosmos. Right at the heart of the Whirlpool Galaxy, like in most large galaxies, sits a supermassive black hole. This cosmic behemoth is incredibly massive, millions of times the mass of our Sun, and it's surrounded by a swirling disk of gas and dust called an accretion disk. As material spirals into the black hole, it heats up to extreme temperatures, emitting vast amounts of radiation. But this black hole has a peculiar secret. It's shooting out a jet of high-energy particles, not straight out from the poles as we typically see, but at a strange, tilted angle. Imagine a spinning top that's wobbling, its axis not perfectly vertical. That's kind of what's happening with this black hole's jet. This unusual alignment has puzzled scientists. We generally expect these powerful jets to be launched perpendicular to the accretion disk, aligned with the black hole's spin axis. The Whirlpool Galaxy's black hole seems to be breaking the rules, or at least, it's revealing a more complex reality about how these jets are formed and influenced. This off-kilter jet challenges our standard models of how black holes behave and how they interact with their surroundings. It suggests that there might be other forces at play, perhaps related to the galaxy's dynamic environment or the history of material falling into the black hole. One possibility is that the magnetic fields around the black hole are twisted or misaligned, forcing the jet to erupt at an angle. Magnetic fields are thought to play a crucial role in launching and collimating these powerful jets, focusing the particles into narrow beams that can extend for thousands of light years. The unusual angle of the jet in the Whirlpool Galaxy provides a unique opportunity to study these magnetic fields and understand their geometry and strength in a way that's difficult with more conventionally aligned jets. It's like getting a skewed perspective that, paradoxically, helps us see the whole picture more clearly. Scientists are using radio telescopes and X-ray observatories to map these magnetic fields and see if they can find evidence of this misalignment. The tilted jet could also be a sign that the black hole's spin axis is not aligned with the accretion disk, a phenomenon known as a warped disk, which can happen when new material is added to the disk from a different direction, perhaps from the companion galaxy. This scenario paints a picture of a violent, chaotic core, where the relentless inflow of matter creates a complex and unpredictable environment around the central black hole. Understanding this peculiar jet is key to unlocking secrets about the inner workings of supermassive black holes and their influence on the galaxies they inhabit. Zooming out from the turbulent center, we encounter one of the Whirlpool Galaxy's most visually striking features, its iconic spiral arms, which are not uniformly colored. In certain regions, these majestic arms glow with a peculiar reddish hue, a visual anomaly that stands out against the more typical blues and whites of star-forming regions. This isn't just a trick of the light or an artifact of the image. The faint ruby tones signal something fundamental about the material within those specific sections of the spiral structure. Normally, the vibrant blue light we see emanating from spiral arms comes from hot, young, massive stars that are burning brightly and quickly, illuminating the surrounding gas and dust. The white areas are a mix of these hot stars and older, cooler ones, but the patches of red suggest a different story. One theory is that the unusual color is caused by the composition of the dust in those regions. Interstellar dust, the tiny grains of silicates and carbon that float between stars, can absorb and scatter light differently depending on its size and composition. Perhaps the dust in these red regions has a unique chemical makeup or grain size distribution that causes it to scatter blue light away while allowing red light to pass through, making the area appear red when viewed from our perspective. Think about how dust in our own atmosphere can make sunsets appear red. It's a somewhat similar principle, although on a vastly larger cosmic scale. Another possibility is related to the type of stars present in these red areas. While the bright blue light comes from newborn stars, there might be a higher concentration of evolved stars in these particular parts of the Whirlpool's arms. As stars age, they cool down and their light shifts towards the red end of the spectrum. Red giants and red supergiants, for example, are much cooler and redder than the hot, young blue stars. If these regions have experienced a burst of star formation in the more distant past, say millions of years ago, the most massive and bluest stars would have already died out, leaving behind a population of older, redder stars that now dominate the light output. It would be like looking at a forest where the fast-growing saplings have been cleared, leaving only the mature, slow-growing trees. This scenario suggests that the star formation history in these patches is different from the rest of the spiral arms, perhaps influenced by local conditions or the gravitational interaction with the companion galaxy. The companion galaxy's tidal forces could be triggering star formation in some areas while inhibiting it in others, leading to variations in the age and type of stars found in different parts of the spiral arms. Studying the specific properties of the starlight from these red regions, such as its spectrum, can help astronomers determine the ages and types of stars present and see if they match the predictions of this theory. A third intriguing explanation for the red patches involves the rate of star formation itself. While the blue regions clearly indicate active star formation, the red areas might be places where star formation is either slower or has recently tapered off. When star formation is ongoing, the intense ultraviolet light from the newly formed blue stars excites the surrounding hydrogen gas, causing it to emit light in the red part of the spectrum, specifically a wavelength known as hydrogen alpha. This is why star-forming regions are often associated with pinkish or reddish nebulae. However, if there are fewer massive young stars, or if the star formation process has slowed down, the intensity of this red emission would be lower. This could explain the presence of a fainter, less dominant red hue compared to the vibrant pink of active star-forming knots. It's a subtle distinction, but one that can provide valuable clues about the conditions within those specific parts of the galaxy. Future observations with instruments that can analyze the light in very specific wavelengths, like spectrographs, will be crucial in unraveling the mystery of the Whirlpool's red spiral arms and understanding the complex interplay of dust composition, stellar populations, and star formation rates that gives this galaxy its unique and captivating appearance. Away from the main body of the Whirlpool Galaxy, there's an almost invisible feature that's captivated astronomers, a vast, ghostly cloud of hydrogen gas floating seemingly detached in space. It's not a part of the prominent spiral arms, nor is it clearly feeding into the galaxy in a visible stream. This massive cloud, detected through its radio emissions, contains an enormous amount of raw material, enough to form billions of stars. Its presence so far out from the main galactic disk, yet gravitationally linked, poses a significant puzzle. How did it get there, and what is its purpose in the cosmic scheme of things? One compelling hypothesis ties the cloud's existence to the Whirlpool Galaxy's ongoing interaction with its smaller companion, NGC 5195. Remember that gravitational tug-of-war we talked about? It's a violent dance capable of stripping gas and dust from both galaxies through tidal forces. Imagine two dancers holding hands and spinning rapidly. Sometimes a piece of their clothing might be flung outwards. On a galactic scale, these tidal forces can pull vast amounts of interstellar gas away from the main body of a galaxy, forming long, trailing structures called tidal tails. This ghostly hydrogen cloud could be a remnant of such a tidal interaction, a massive blob of gas that was ripped out of either the Whirlpool or its companion during a close pass millions of years ago. Over time, this ejected gas could have cooled and condensed, forming the cloud we observe today. It's like a cosmic bruise left behind from a past close encounter, a silent witness to the violence of galactic mergers and interactions. Another intriguing possibility for the origin of this detached cloud involves a more ancient event, a past collision with another galaxy entirely. The Whirlpool Galaxy has a complex history, and it's likely been involved in multiple encounters and mergers over billions of years. Perhaps this hydrogen cloud is the leftover debris from a smaller galaxy that was completely consumed by the Whirlpool long ago. When galaxies merge, the gravitational forces can scatter gas and stars into the surrounding space, creating vast halos and streams of material. This cloud could be a particularly large and dense clump of gas that was flung outwards during such a merger, remaining relatively intact in the galactic outskirts. It's a fascinating idea that suggests the Whirlpool's history is deeply intertwined with the fates of other, now vanished galaxies. studying the velocity and distribution of the gas within the cloud could provide clues about its origin. If the gas is moving in a way that seems disconnected from the current dynamics of the whirlpool and its companion, it might support the idea of a more distant, ancient event. A more speculative and perhaps more mysterious explanation for the ghostly hydrogen cloud involves the influence of dark matter. Dark matter, the invisible substance that makes up the majority of the mass in the universe, is thought to form vast halos around galaxies, providing the gravitational scaffolding that holds them together. While we can't see dark matter directly, its gravitational effects are evident. Could this detached hydrogen cloud be somehow held in place or even formed within a substructure of the whirlpool's dark matter halo? Perhaps there's a localized clump of dark matter in that region of space, providing the extra gravitational pull needed to keep such a massive gas cloud from either falling into the whirlpool or dispersing into extragalactic space. It's a tantalizing prospect that could offer insights into the distribution and properties of dark matter on smaller scales. However, proving a direct link between the cloud and a dark matter substructure is incredibly challenging, as we can only infer the presence of dark matter through its gravitational effects on visible matter. Nevertheless, the sheer size and isolated nature of this hydrogen cloud make it a prime candidate for exploring the potential influence of dark matter in shaping the outer regions of galaxies. Regardless of its origin, this ghostly hydrogen cloud represents a vast reservoir of potential star-forming material waiting in the cosmic wings. Will it eventually fall into the Whirlpool Galaxy, fueling a new burst of star formation? Or will it remain forever a detached enigma, a silent monument to the complex and often violent processes that shape the universe? Its mystery serves as a powerful reminder that even in well-studied galaxies like the Whirlpool, there are still profound secrets waiting to be uncovered. Adding another layer to the Whirlpool Galaxy's strangeness is something truly extraordinary. It's hosted not one, but two observed supernova explosions within a span of just over a decade. Supernova are the catastrophic deaths of massive stars, events so powerful they can outshine an entire galaxy for a short time. They are relatively rare occurrences in any single galaxy. The Milky Way, for example, might see 1 or 2 detectable supernova per century on average. Yet, the Whirlpool Galaxy gave us 2 front-row seats to these cosmic fireworks in relatively quick succession: Supernova 1994I and Supernova 2005 EFF. This frequency is highly unusual and begs the question: what makes the Whirlpool Galaxy such a prolific factory for these stellar detonations? The appearance of 2 supernovas so close together in time tells us something significant about the rate of star formation and the types of stars being born in M51. Supernova that are visible to us typically come from 2 main types of stars. One type is the core collapse supernova, which occurs when a massive star, many times the mass of our Sun, runs out of nuclear fuel in its core. The core collapses under gravity, triggering a runaway implosion that results in a colossal explosion. These massive stars live fast and die young. They burn through their fuel in just a few million years, a blink of an eye in cosmic terms. The other type is a Type 1, a supernova, which happens in a binary system involving a white dwarf star that accumulates material from its companion until it reaches a critical mass and explodes. While both types contribute to the overall supernova rate, the frequent core collapse supernova are a strong indicator of ongoing, vigorous star formation. The more massive stars a galaxy produces, the higher the chance of observing these dramatic deaths. The fact that the Whirlpool Galaxy has hosted 2 supernova so recently suggests that it is forming massive stars at a relatively high rate. This isn't entirely surprising given its interaction with the companion galaxy, NGC 5195. Galactic collisions, even glancing blows or close passes like the one M51 is experiencing, compress gas and dust, triggering waves of star formation throughout the interacting galaxies. Imagine squeezing a sponge. The water is forced out. Similarly, the gravitational forces between the two galaxies are compressing vast clouds of interstellar gas and dust, the raw materials for stars. This compression leads to the formation of dense regions where gravity can more easily pull material together to form new stars, including the massive ones that will eventually explode as supernova. The tidal tails and distorted spiral arms of the whirlpool are visual evidence of this compression and the resulting star formation. Each supernova observed provides us with a snapshot of this stellar birthing process, a powerful reminder of the dynamic and sometimes violent cycles of creation and destruction happening within the galaxy. Supernova are not just spectacular in points, they are also crucial for the chemical enrichment of galaxies. The elements heavier than helium, including carbon, oxygen, iron, and many others that make up planets and even ourselves, were forged in the cores of stars and dispersed into space by supernova explosions. The relatively high supernova rate in the Whirlpool Galaxy means it's actively recycling heavy elements back into the interstellar medium, providing the building blocks for future generations of stars and potentially planets. Analyzing the light curves and spectra of supernova 1994I and supernova 2005 EFF has provided astronomers with valuable data about the conditions in the specific regions where they occurred. For instance, by studying the type of supernova, we can confirm whether it was a core collapse event from a massive star or a type 1, an event involving a white dwarf. The spectra, which is like a cosmic fingerprint of the light, can reveal the elemental composition of the exploded star's outer layers and the surrounding material, offering clues about the star's history and the environment it was born in. These observations help astronomers refine their models of stellar evolution and supernova explosions, improving our understanding of these fundamental cosmic processes. The locations of these two supernovae within the Whirlpool Galaxy are also significant. Were they in the dense inner regions near the nucleus or further out in the spiral arms? Their positions can tell us about where the most active star formation is taking place within the galaxy and how the interaction with the companion galaxy might be influencing star birth in different areas. The fact that we observed two within such a short period underscores the incredibly active and dynamic nature of the Whirlpool Galaxy, a cosmic crucible where stars are born and die at a pace that's unusually high. It makes us wonder how many other supernovae have occurred in M51 that we missed because they happened on the far side of the galaxy or were obscured by dust. The two we saw are likely just a small sample of the ongoing cycle of stellar death and rebirth in this fascinating galactic system. One of the most puzzling observations in the Whirlpool Galaxy isn't a bright star or a swirling arm, but something far more subtle. A diffuse glow of X-rays extending out into the space surrounding the galaxy, forming what astronomers call an X-ray halo. It's like the galaxy is wrapped in an invisible cloak of high-energy radiation, a phenomenon that hints at powerful processes happening just beyond our immediate view. This X-ray glow isn't coming from specific point sources like black holes or neutron stars. Instead, it's spread out, indicating a vast volume of extremely hot gas. To emit X-rays, gas needs to be heated to millions of degrees, far hotter than the gas found within the galaxy's disk or even in typical star-forming regions. So, where is this superheated gas coming from, and what is heating it? One leading theory points to the cumulative effect of countless supernova explosions that have occurred within the Whirlpool Galaxy over billions of years. Remember those spectacular stellar deaths we just talked about? When massive stars explode, they don't just create beautiful nebulae, they also blast enormous amounts of energy and material into the surrounding space. This material includes not only the elements forged in the star's core, but also a shockwave that heats the interstellar gas to incredibly high temperatures. Over vast timescales, the combined energy and material from millions of supernovae could have blown huge bubbles of hot gas out of the galactic disk, pushing it into the halo. Think of it like a galactic wind driven by the relentless activity of dying stars. This supernova-heated gas would then expand and cool as it moves away from the galaxy, but a significant portion of it could remain hot enough to emit X-rays for a long time, creating the extended halo we observe. The presence of this X-ray halo provides compelling evidence for the dramatic impact that supernova feedback has on the evolution of galaxies. It's not just about dispersing heavy elements, it's also about redistributing vast quantities of energy and matter, shaping the galaxy's structure and influencing future star formation. The extent and brightness of the X-ray halo can give us clues about the total energy output of supernova in the Whirlpool's history and how efficiently this energy has been transferred to the surrounding gas. Analyzing the spectrum of the X-ray emission can also reveal the chemical composition of the hot gas, telling us about the types of elements that were ejected from those ancient supernova. However, supernova might not be the whole story. The gravitational dance between the Whirlpool Galaxy and its companion, NGC 5195, could also be playing a crucial role in creating and shaping the X-ray halo. As the two galaxies interact, their gravitational pull on each other can compress and shock the gas in their outer regions, heating it to X-ray emitting temperatures. This is similar to how a tidal wave heats up as it crashes onto the shore, but on a cosmic scale. The interaction could also be stripping gas from both galaxies, flinging it out into the surrounding space where it becomes part of the hot halo. The fact that the X-ray halo is spread out and somewhat irregular in shape might be a sign of this ongoing interaction, with tidal forces pulling and pushing the hot gas around. It's a dynamic process, a constant churning and mixing of material driven by the gravitational embrace of the two galaxies. Furthermore, the supermassive black hole at the center of the Whirlpool Galaxy, with its peculiar tilted jet, could also be contributing to the X-ray halo. While the jet itself is a focused beam of high-energy particles, the energy it releases as it interacts with the surrounding gas can heat that gas to X-ray temperatures. Think of a powerful laser beam passing through smoke. It heats and illuminates the particles within the smoke. Similarly, the black hole's jet could be injecting energy into the galactic halo, contributing to the overall X-ray glow. The unusual angle of the jet might even be influencing the shape and distribution of the hot gas in the halo, creating asymmetries or specific features that wouldn't be there if the jet were perfectly aligned. It's a complex interplay of forces and events, with supernova, galactic interactions, and possibly the central black hole all contributing to the formation and maintenance of this enigmatic X-ray halo. Studying this diffuse X-ray emission provides a unique window into the history of the Whirlpool Galaxy, revealing the long-term consequences of stellar activity and galactic interactions on the distribution and state of matter in the vast space surrounding the galaxy. Perhaps one of the most perplexing aspects of the Whirlpool Galaxy involves something we can't even see: dark matter. While it's widely accepted that galaxies are embedded within vast halos of this mysterious substance, observations of M51 suggest it might have significantly less dark matter than our current models predict for a galaxy of its size and type. This isn't just a minor discrepancy. It's a potential challenge to our fundamental understanding of galactic structure and the distribution of dark matter in the universe. How do we measure dark matter if we can't see it? We infer its presence and amount by observing its gravitational effect on visible matter like stars and gas. Stars orbiting in the outer regions of a spiral galaxy should be moving slower if the galaxy's mass is dominated by the visible matter in the disk. However, they are often observed to orbit much faster, as if there's extra, unseen mass providing the gravitational pull. This extra mass is attributed to dark matter. In the case of the Whirlpool Galaxy, when astronomers measure the rotation speed of gas and stars in its outer regions, the speed seemed to drop off more quickly than expected if it had a typical dark matter halo. It's like measuring the weight of a mysterious box by how quickly a marble rolls down its side. If the marble slows down faster than expected, the box must be lighter. In M51, the rotation curves suggest a less massive dark matter halo than would be predicted based on the galaxy's visible mass and typical galactic formation scenarios. One possible explanation for this apparent deficit of dark matter is that our measurements are somehow flawed. Measuring the rotation of galaxies, especially at the very edges, is a complex task. It involves observing the Doppler shift of light from stars and gas to determine their velocity relative to us. Small errors in measurement, uncertainties in distance estimates, or assumptions about the geometry of the galaxy could potentially influence the results. Perhaps the observed drop-off in rotation speed is due to limitations in our observational techniques or data analysis, rather than an actual lack of dark matter. Astronomers are constantly refining their methods and using different techniques, like gravitational lensing, the bending of light from distant objects by the galaxy's gravity, to independently verify their measurements of mass distribution. If future, more precise observations confirm the low dark matter content, it would strengthen the case that this isn't just a measurement error. It's a meticulous process, constantly checking and rechecking the data, like a detective examining every possible angle of a complex case. Another compelling explanation, tied to the Whirlpool Galaxy's ongoing interaction with its companion, is that the dark matter has been tidally stripped away. Galactic collisions and close encounters are incredibly disruptive events. Just as tidal forces can pull out streams of gas and stars, they can also strip away dark matter from the outer halo of a galaxy. Imagine two fuzzy balls passing close to each other. Some of the outer fuzz might be pulled off. The smaller companion galaxy, NGC 5195, is likely embedded within its own dark matter halo, and the gravitational interaction could be pulling dark matter away from the whirlpool's outer regions. This tidal stripping would reduce the overall amount of dark matter in M51, particularly in its outer parts where the gravitational influence of the companion is strongest. The visible galaxy, which is more tightly bound by its own gravity, would be less affected, leading to the observed discrepancy between the visible and dark matter distribution. This scenario is supported by simulations of interacting galaxies, which show that tidal forces can indeed significantly alter the distribution of dark matter. It suggests that the apparent lack of dark matter in M5 pool might not be intrinsic to the galaxy itself, but a consequence of its violent history. However, if careful measurements rule out both errors and tidal stripping as the sole explanations, the low dark matter content of the Whirlpool Galaxy could represent a more profound challenge to our current cosmological models. Standard cold dark matter theory, which is the prevailing model, predicts that galaxies like the Whirlpool should have a substantial dark matter halo. If M51 truly has significantly less dark matter than expected, it might force us to reconsider some of the fundamental assumptions of this theory. Could dark matter interact with itself in ways we don't yet understand, leading to different distributions in some galaxies? Could the properties of dark matter not be uniform across the universe? Or, in a more radical scenario, could there be something fundamentally wrong with the way we understand gravity on galactic scales, making dark matter appear to be missing when it's not? While the vast majority of evidence supports the existence of dark matter, anomalies like the potential deficit in the Whirlpool Galaxy are crucial for pushing the boundaries of our knowledge and refining our theories. Astronomers are actively studying M51, using every tool at their disposal to try and determine the true amount and distribution of dark matter within it. The answer could either confirm our current understanding of the universe or point us towards a revolutionary new direction in physics and cosmology. The mystery of the Whirlpool's missing dark matter remains a compelling puzzle, a reminder that even with our most advanced instruments, the cosmos still holds secrets that can overturn our most cherished ideas. As we marvel at the grand design of the Whirlpool Galaxy, our eyes are drawn to the intricate dust lanes crisscrossing its spiral arms. In typical spiral galaxies, these lanes of cool, dense gas and dust are usually smooth and follow the graceful curve of the arms like dark rivers flowing through a starry landscape. They are the nurseries of stars, the places where raw material is dense enough to collapse under gravity and ignite nuclear fusion. But in the whirlpool, these dust lanes tell a story of disruption and violence. They are not always smooth. Instead, they appear warped, twisted, and sometimes even broken, as if the galaxy's internal structure has been pulled and contorted by an unseen hand. Imagine taking a beautifully spun piece of yarn and tugging at different points. The smooth curves would become distorted and tangled. That's what's happening to the whirlpool's dust lanes, and the culprit is likely its gravitational dance partner, the companion galaxy NGC 5195. The strong gravitational pull from the smaller galaxy is acting like a cosmic sculptor, pulling and pushing on the whirlpool's disk, particularly the outer regions where the dust lanes reside. This tidal force distorts the galaxy's gravitational potential, the underlying landscape of gravity that holds everything together. As the gas and dust clouds orbit the galactic center, they encounter these distortions, causing their paths to deviate from simple circles and resulting in the observed warping and twisting. Think of it like driving on a road that suddenly has unexpected bumps and turns. Your vehicle's path won't be as smooth as it would be on a perfectly level road. The gas and dust in the whirlpool are encountering these gravitational bumps created by the companion galaxy's influence, and their response is to twist and distort their usual patterns. These warped dust lanes are visual evidence of the ongoing gravitational interaction, a visible scar left on the face of the galaxy by its close encounter. By studying the specific patterns of the warping, astronomers can gain insights into the strength and nature of the gravitational forces at play. The degree of distortion, the direction of the twists, and the extent of the affected regions can all provide valuable data points for computer simulations that model galactic interactions. These simulations help us understand how galaxies behave when they get close to each other and how their structures are reshaped by tidal forces. Comparing the observed warped dust lanes in the whirlpool with the predictions of these simulations allows astronomers to refine their models and get a better handle on the dynamics of galactic mergers and close encounters. Furthermore, the presence of these disturbed dust lanes has implications for star formation within the Whirlpool Galaxy. Dust lanes are, as we mentioned, the sites of star birth. When they are compressed and distorted by gravitational forces, it can trigger an increase in star formation activity. The compression of the gas and dust clouds makes them denser, making it easier for gravity to overcome the internal pressure and initiate the collapse that leads to the formation of new stars. This is why interacting galaxies are often observed to have higher rates of star formation than isolated galaxies. The gravitational disturbance acts as a catalyst for stellar nurseries to spring to life. The warped dust lanes in the whirlpool are likely areas where this enhanced star formation is occurring, contributing to the galaxy's overall higher supernova rate. The twisting and tangling of the lanes could be creating localized regions of higher density, leading to bursts of star formation in specific areas along the spiral arms. It's a chain reaction. The gravitational pull of the companion distorts the dust lanes. The distorted dust lanes become denser, and the denser dust lanes become more fertile ground for the birth of new stars. The warped dust lanes also pose challenges and opportunities for astronomers trying to map the distribution of gas and dust in the Whirlpool Galaxy. Their irregular shapes and orientations make it more difficult to create accurate three-dimensional maps of the galaxy's structure. However, they also serve as unique tracers of the gravitational field and the history of the interaction. By carefully mapping the distribution and velocity of the gas within these warped lanes, astronomers can piece together the history of the interaction and understand how the companion galaxy has influenced the whirlpool over millions of years. It's like trying to reconstruct the path of a disturbance by looking at the ripples it left behind on a pond. The warped dust lanes are those ripples, providing a visual record of the gravitational forces that have shaped this stunning spiral galaxy. Their very irregularity is a source of fascination and information, a testament to the dynamic and often violent processes that drive galactic evolution. Peering even closer into the dynamic environment of the Whirlpool Galaxy reveals another fascinating anomaly: the presence of what appear to be runaway star clusters. These aren't just individual stars zipping through space. These are entire groups of hundreds, sometimes even thousands, of young stars that seem to have been violently ejected from their birthplace in the galaxy's spiral arms and are now hurtling through the galactic halo at incredible speeds. Imagine a handful of marbles being flicked out of a spinning wheel. That's the sort of energetic expulsion we're talking about on a cosmic scale. Finding young star clusters far from the dense gas and dust where stars are born is unusual. Star clusters typically form within giant molecular clouds in the galactic disk and remain gravitationally bound to the disk as they age. Their presence in the outer regions, traveling at speeds that could eventually carry them out of the galaxy entirely, suggests they experienced a powerful kick, a significant gravitational or energetic event that propelled them outwards. The youth of these clusters is key. It tells us that the event that ejected them happened relatively recently, within the last few million years, which is the typical lifespan of the massive stars that dominate young clusters before they explode as supernova. So, what provided the immense force needed to launch these stellar nurseries into the galactic void? One leading candidate for the culprit is the ongoing gravitational interaction between the Whirlpool Galaxy and its companion, NGC 5195. As the two galaxies dance, the constantly changing gravitational forces can create localized tidal surges and gravitational slingshots. Think of how a smaller object can be whipped around a much larger one in orbit, gaining speed in the process. In the chaotic environment of a galactic close encounter, dense regions of gas and stars can experience sudden, strong gravitational boosts from the passing companion galaxy. If a particularly compact and massive star cluster is in the wrong place at the wrong time, a close pass by the companion galaxy, or even a dense clump within the companion, could provide the necessary gravitational impulse to eject the cluster from the whirlpool's disk and send it speeding outwards into the halo. This scenario provides a compelling link between the observed runaway clusters and the overall dynamic state of the whirlpool system. The energy of the galactic interaction is being transferred to these stellar groups, manifesting as their high velocities. Another intriguing possibility is that some of these runaway clusters were ejected by powerful events within the spiral arms themselves, perhaps involving the supermassive black hole at the galaxy's center, or even interactions with intermediate mass black holes that might reside in the spiral arms. While intermediate mass black holes, those with masses between a few hundred and 100,000 times that of our Sun, are still theoretical in many cases, some astronomers speculate they could exist within dense star clusters. If a young star cluster contained or encountered such a black hole, the intense gravitational forces could significantly disrupt the cluster and potentially eject some of its constituent stars or even the entire cluster if the interaction is violent enough. Imagine a dense cluster of stars orbiting a massive object. If that object is a black hole, the stars closest to it could be accelerated to extremely high speeds and potentially flung out of the cluster and the galaxy. This is a more speculative idea, as direct evidence for intermediate mass black holes in star clusters is scarce, but it remains a possibility in such a dynamically active galaxy. Furthermore, the powerful jets emanating from the central supermassive black hole, even the oddly tilted one we discussed earlier, could potentially interact with dense star-forming regions or young clusters if their paths intersect. While less likely to eject entire clusters as a primary mechanism compared to gravitational interactions, the sheer energy and momentum of these relativistic jets could potentially contribute to disrupting and accelerating material in the galactic disk, perhaps providing an additional kick to clusters already destabilized by tidal forces. It's a complex picture where multiple energetic processes could be conspiring to create these runaway stellar systems. The existence of these runaway star clusters is a powerful indicator of the violent and dynamic processes at work in the Whirlpool Galaxy. They are like cosmic cannonballs fired from the heart of galactic interaction and stellar activity. Studying their trajectories, velocities, and the properties of the stars within them can provide valuable clues about the specific events that launched them and the conditions in the regions where they were born. Their journey through the galactic halo also offers a unique opportunity to study how star clusters evolve when they are removed from the dense environment of the galactic disk and exposed to the less dense conditions of the halo. They might eventually dissipate with their stars spreading out into the halo, or they could remain gravitationally bound for a longer time. The mystery of their ejection highlights the incredible forces that shape galaxies and the surprising ways in which stellar systems can be flung from their homes. Adding to the list of strange things in the Whirlpool Galaxy are enormous, bubble-like structures detected not in visible light but in radio waves. These aren't soap bubbles floating in space. These are vast expanses of radio emission, appearing like inflated spheres extending far beyond the galaxy's visible disk. Seeing these radio bubbles is like discovering hidden cavities within the galaxy, filled with energetic particles that are emitting radiation at radio frequencies. They are evidence of powerful, large-scale events that have injected tremendous amounts of energy into the space around the galaxy. What could possibly create such colossal structures? One compelling explanation ties these radio bubbles to ancient outbursts from the supermassive black hole at the galaxy's center. Supermassive black holes aren't always quietly consuming matter. Sometimes they go through active phases where they gobble up large amounts of gas and dust, and during these feasts they can launch powerful jets of plasma outwards. These jets, moving at nearly the speed of light, can extend for vast distances, and as they plow through the surrounding interstellar medium, they can inflate giant lobes or bubbles of hot, radio-emitting gas. It's like a cosmic blowtorch carving out cavities in the galaxy's structure. The size of these bubbles suggests that the outbursts that created them must have been incredibly powerful and sustained over long periods, perhaps millions of years ago. The radio waves we detect from these bubbles are produced by electrons spiraling in magnetic fields, a process known as synchrotron radiation, which is a signature of high-energy particles interacting with magnetic fields. The presence of these radio bubbles is a fossil record of past activity from the Whirlpool's central black hole, providing evidence that it has gone through more active phases in its history than it is currently in. Studying the size, shape, and distribution of these bubbles can give astronomers insights into the power and duration of these ancient black hole eruptions. Another potential source for the energy inflating these radio bubbles is widespread starburst activity throughout the galaxy. We know the Whirlpool is currently experiencing enhanced star formation due to its interaction with its companion galaxy. But perhaps in the past there were even more intense bursts of star formation, so-called starbursts, where stars were being born at an incredibly rapid rate across large regions of the galaxy. When massive stars explode as supernova, they release vast amounts of energy and create powerful shock waves. In a starburst region where supernovae are occurring frequently and in close proximity, these shock waves can combine and create a super wind that blows gas and cosmic rays out of the galactic disk. This outflowing material, including energetic particles and tangled magnetic fields, can then inflate giant bubbles in the surrounding halo, which would be visible in radio waves. Think of it like many small explosions joining together to create one giant blast that pushes material outwards. If the Whirlpool experienced a major starburst phase in its past, potentially triggered by an earlier, closer pass with its companion galaxy or even a minor merger, this could have generated enough energy to inflate the large radio bubbles we observe today. Distinguishing between whether the bubbles were inflated by the central black hole or by widespread star formation can be challenging, but astronomers look for clues in the shape and location of the bubbles, as well as the properties of the radio emission. Black hole jets tend to be more collimated initially and can produce more elongated lobes, often centered around the galactic nucleus. Starburst-driven winds tend to be more diffuse and can originate from broader regions within the galactic disk. The spectrum of the radio emission can also provide hints about the origin of the energetic particles. However, it's also possible that both processes have contributed to the formation of the radio bubbles in the Whirlpool Galaxy. The galaxy's dynamic environment, with its active black hole and ongoing interaction-induced star formation, provides multiple potential sources of the energy needed to create these vast structures. The discovery of these radio bubbles reminds us that galaxies are not static objects, but are constantly being shaped by powerful internal and external forces. These invisible radio structures are a testament to the energetic history of the Whirlpool Galaxy, revealing past epochs of intense activity from its core or its stellar populations. They are a reminder that what we see in visible light is only part of the story, and by observing the universe in different wavelengths, we can uncover hidden features and processes that are crucial to understanding galactic evolution. Delving even deeper into the very heart of the Whirlpool Galaxy, we encounter one of its most persistent and baffling mysteries, the appearance of not one, but seemingly two bright points of light at its core. For years, astronomers have been captivated by these so-called twin nuclei, two distinct sources of intense emission located very close to each other within the galactic center. It's like the galaxy has a double heart, each beating with a fierce energy that stands out among the surrounding stars and gas. At first glance, the most exciting explanation, and one that has been widely speculated, is that these twin nuclei are actually two supermassive black holes locked in a cosmic dance, perhaps on their way to merging. We know that galactic collisions can lead to the merger of their central black holes, and the Whirlpool Galaxy is clearly in the process of interacting with its companion. A binary supermassive black hole system in the core of M51 would be a monumental discovery, providing a unique laboratory to study how these colossal objects interact and eventually coalesce, a process predicted by general relativity and thought to be a major source of gravitational waves. The immense gravitational pull of two black holes circling each other would also have profound effects on the gas, dust, and stars in the galactic core, potentially explaining some of the other strange phenomena observed there. Observing the orbital motion of these purported twin black holes, if they are indeed a pair, would allow astronomers to test our understanding of gravity in extreme conditions and provide critical data for gravitational wave detectors like LIGO and Virgo, which are designed to detect the ripples in spacetime created by the merger of black holes. It's a thrilling prospect, the idea of witnessing two of the universe's most enigmatic objects spiraling towards a cataclysmic union. However, the appearance of twin nuclei may not be as dramatic as it seems. Another, perhaps less exciting but scientifically equally valuable, explanation is that one of the bright points is simply a light echo or reflection caused by uneven distribution of dust around a single central supermassive black hole. Imagine shining a flashlight into a dusty room. The beam of light can scatter off the dust particles, making it appear as if the light is coming from multiple points or creating bright patches where the dust is denser. In the core of a galaxy, there are vast amounts of gas and dust swirling around the central black hole. If this dust is not distributed uniformly, If there are dense clumps or structures within the accretion disk or the surrounding material, they could be reflecting or scattering the intense light and X-rays produced by the black hole and its accretion disk. This scattered light, when observed by telescopes, could create the illusion of a second bright nucleus, even if there is only one energy source at the very center. It would be like seeing a reflection in a mirror and thinking there's a second object. Distinguishing between a true binary black hole system and a light echo from dust is incredibly challenging and requires very high-resolution observations across multiple wavelengths of light. Astronomers are using instruments like the Hubble Space Telescope and ground-based adaptive optics systems to try and resolve the structure of these twin nuclei with the greatest possible detail. They are also observing the core in different wavelengths, from radio waves to X-rays, because dust scatters and absorbs light differently at various wavelengths. If the second nucleus is a light echo, its appearance and brightness might change depending on the wavelength observed, or it might show signs of scattered light rather than direct emission from a compact source. Furthermore, if they are a true binary system, the 2 points of light should exhibit orbital motion around each other over time, though this motion could be very slow depending on their separation and masses. Detecting this orbital movement would be definitive proof of a binary black hole. However, the predicted orbital period for 2 supermassive black holes at that separation might be millions of years, making it incredibly difficult to observe significant changes in our lifetime. The mystery of the Whirlpool's twin nuclei remains an active area of research, a compelling puzzle that highlights the challenges of peering into the obscured and dynamic cores of galaxies. Unraveling whether we are seeing 2 black holes wrestling for dominance or a cosmic optical illusion caused by dust will provide crucial insights into the nature of galactic centers and the powerful objects that reside within them. Venturing further out into the cosmic neighborhoods of the Whirlpool Galaxy, we encounter some particularly peculiar residents. Not just the runaway star clusters we discussed, but entire clusters of stars that are unusually blue and found far above or below the galaxy's main disk. These aren't your typical globular clusters, which are ancient, reddish collections of stars found in galactic halos. These are younger, distinctly bluer star clusters, and their location so far from the galactic plane is a significant anomaly. Their blue color tells us they contain a significant population of young, hot, massive stars that are burning brightly, a characteristic of recently formed or relatively young stellar populations. Finding young star clusters so far out in the galactic halo is unexpected, as star formation typically occurs in the dense gas and dust concentrated in the galactic disk. So, what are these blue outliers, and how did they end up in such an unusual place? One intriguing possibility is that these blue clusters are actually the remnants of much smaller dwarf galaxies that have been captured and are in the process of being cannibalized by the much larger Whirlpool Galaxy. Dwarf galaxies are small, faint galaxies that orbit larger ones. They are thought to be numerous in the universe and are often found in galactic groups and clusters. In galactic interactions and mergers, larger galaxies often gravitationally pull in and eventually absorb smaller ones, as a dwarf galaxy is tidally disrupted by the gravitational forces of a larger galaxy. Its stars and gas can be stripped away, forming streams and clumps of material that are dispersed into the larger galaxy's halo. Some of the denser, more gravitationally bound parts of the dwarf galaxy, like its star clusters, might survive the disruption process for a while, orbiting within the larger galaxy's halo before eventually being fully integrated or pulled into the disk. If these captured dwarf galaxies were actively forming stars before their encounter with the Whirlpool, they would contain young, blue star clusters. These clusters, held together by their own gravity, could persist in the Whirlpool's halo as the rest of the dwarf galaxy is ripped apart. The presence of multiple such blue outliers in the Whirlpool's halo could be evidence that it has captured and is currently digesting several smaller galaxies, a common process in galactic evolution. Each blue cluster would be a surviving fragment, a relict of a smaller cosmic system that has met its end in the embrace of the larger whirlpool. Another compelling explanation is that these blue outliers are not captured entities, but were violently ejected from the Whirlpool Galaxy itself during a past, even more violent merger event. While the current interaction with NGC 5195 is significant, it is possible that the Whirlpool experienced a major merger with a more substantial galaxy in its earlier history. Such a powerful collision would have sent shockwaves throughout the galaxy, compressing gas and triggering widespread star formation. It would also have subjected stellar systems to intense gravitational forces. In the chaotic aftermath of such a merger, dense clumps of newly formed stars or existing young star clusters could have been gravitationally slingshotted out of the galactic disk and propelled into the halo at high velocities. Similar to how the current interaction might be creating runaway clusters, a past, more energetic merger could have ejected these blue clusters to much greater distances and left them orbiting in the halo. The blue color again points to their relative youth, consistent with them having formed during a merger-induced starburst rather than being ancient, captured systems. Distinguishing between these two scenarios, captured dwarf galaxy remnants versus ejected star clusters, can be challenging. Astronomers study the chemical composition of the stars within these blue clusters. The elemental abundance of stars in dwarf galaxies can sometimes be different from those in a larger galaxy like the Whirlpool. If the stars in the blue outliers have a chemical signature that is distinct from the typical stars in the Whirlpool's disk or halo, it would support the idea that they originated from a different galaxy. Additionally, astronomers look for signs of stellar populations of different ages within the clusters. A captured dwarf galaxy might contain a mix of older and younger stars, while an ejected cluster formed during a merger might be predominantly young. Mapping the orbits of these blue outliers is also crucial. If they are moving in trajectories that are significantly different from the overall rotation of the Whirlpool's disk and halo, it could be further evidence of an external origin or a violent ejection event. These blue outliers are like cosmic breadcrumbs, providing clues about the Whirlpool Galaxy's tumultuous past and its interactions with other galaxies. They are a reminder that galaxies are not isolated islands, but are constantly interacting, merging, and growing by consuming their smaller neighbors, a process that leaves behind intriguing stellar anomalies far from the familiar structure of the galactic disk. Moving to the realm of the highest energy light, the Whirlpool Galaxy presents another head-scratcher, a specific region within it that glows intensely in gamma rays, forming what astronomers have termed a gamma-ray hotspot. Gamma rays are the most energetic form of electromagnetic radiation, produced by some of the most violent events in the universe, like supernova explosions, the cores of active galaxies, and the decay of radioactive elements. Detecting a concentrated source of gamma rays in a specific area of M51, an area where nothing obvious like a supermassive black hole or a supernova remnant seems to be the clear culprit, is deeply mysterious. It's like finding a spotlight shining in the darkness with no physical lamp in sight. This gamma-ray hotspot stands out against the general background emission from the galaxy, suggesting a localized source of extreme energy production that isn't immediately apparent in other wavelengths. So, what cosmic engine is powering this enigmatic glow? One possibility is that the gamma-ray hotspot is caused by a dense concentration of pulsars. Pulsars are rapidly spinning neutron stars, the incredibly dense remnants of massive stars that have exploded as supernova. Some pulsars emit beams of radiation from their magnetic poles, and if these beams sweep across our line of sight as the star rotates, we detect pulses of radiation across the electromagnetic spectrum, including sometimes in gamma rays. While individual pulsars are typically too faint to be detected as strong gamma-ray sources from the distance of the Whirlpool Galaxy, a region with a particularly high density of these energetic objects could collectively produce enough gamma-ray emission to create a detectable hotspot. The enhanced star formation in the Whirlpool, particularly in areas affected by the galactic interaction, would lead to more massive stars being born and dying as supernova, and thus potentially more neutron stars and pulsars being formed. If star formation has been particularly vigorous in the region corresponding to the gamma-ray hotspot, it might have resulted in a cluster of pulsars packed closely together, their combined gamma-ray output creating the observed glow. It's like having a crowded room full of small light bulbs. Individually, they aren't very bright, but together they can illuminate the space. Astronomers would need to search for evidence of these individual pulsars within the hotspot region using radio telescopes, which are often used to detect the characteristic radio pulses from these objects to see if this explanation holds up. A more exotic and highly speculative explanation for the gamma-ray hotspot involves dark matter annihilation. While we still don't know what dark matter is, some theoretical models propose that dark matter particles could annihilate with each other when they collide, producing high-energy particles and gamma rays. If there is a particularly dense concentration of dark matter in the region of the hotspot, the rate of these annihilation events could be high enough to produce a detectable gamma-ray signal. This is a fascinating but challenging hypothesis to prove. Pinpointing a specific region within a galaxy as a site of enhanced dark matter density is difficult, as dark matter is thought to be smoothly distributed in halos. However, if there are substructures or clumps of dark matter that have survived within the Whirlpool's halo or disk, and if these clumps are located in the region of the hotspot, it could potentially explain the localized gamma-ray emission. Detecting gamma rays with a very specific energy spectrum that matches the theoretical predictions for dark matter annihilation products would be strong, though not conclusive, evidence for this scenario. So far, no such definitive spectral signature has been found in the Whirlpool's gamma-ray hotspot, but the possibility remains a tantalizing prospect that could offer a direct way to detect and study dark matter. A less dramatic but still viable explanation is that the gamma-ray hotspot is caused by the acceleration of cosmic rays in that region. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. When these cosmic rays interact with the interstellar gas and dust in a galaxy, they can produce gamma rays. Regions with intense star formation, supernova remnants, or strong magnetic fields can be efficient accelerators of cosmic rays. If the gamma-ray hotspot in the Whirlpool corresponds to a region where cosmic rays are being particularly efficiently accelerated, or where there is a higher density of interstellar gas for them to interact with, it could explain the increased gamma-ray emission. The ongoing interaction with the companion galaxy is likely creating turbulent conditions in the Whirlpool's interstellar medium, potentially driving powerful shock waves and turbulence that can accelerate particles to high energies. The hotspot could be located in a region where this acceleration is particularly effective, or where the density of the target material, the gas and dust, is higher, leading to more frequent interactions and more gamma-ray production. Distinguishing between these scenarios requires detailed observations across multiple wavelengths and careful analysis of the gamma-ray spectrum to look for signatures that would favor one explanation over the others. The gamma-ray hotspot in the Whirlpool Galaxy serves as a powerful reminder that even seemingly empty or less remarkable regions of a galaxy can be sites of intense, high-energy activity, driven by processes that are not always immediately obvious in visible light. Its mystery continues to push astronomers to explore new possibilities and deploy more sensitive instruments to unravel the secrets hidden within the galaxy's high-energy glow. Adding another layer of intrigue to the core of the Whirlpool Galaxy is its puzzling, flickering behavior. specifically the rapid and unpredictable variations in the brightness of its active nucleus. We expect the region around a supermassive black hole that is actively feeding to be luminous as gas and dust heat up while spiraling inwards. But the whirlpool's core isn't just steadily bright. Its luminosity seems to fluctuate significantly over relatively short timescales, sometimes brightening dramatically and then dimming again within days or even hours. Imagine watching a light bulb that randomly dims and brightens, not on a regular pattern but seemingly erratically. That's what astronomers are observing in the heart of M51, and these flickering changes in brightness are a source of considerable bewilderment as they try to understand the complex processes of black hole feeding. The scale of these variations is important. We're not talking about gradual changes over months or years, which could be explained by larger clumps of material falling into the black hole's accretion disk. The rapid flickering suggests something much smaller and faster is happening very close to the event horizon, the point of no return around the black hole. It indicates dynamic processes occurring on scales comparable to the size of the accretion disk itself, or even within the innermost regions where the extreme gravity of the black hole dominates. These rapid fluctuations in brightness are seen across different wavelengths of light, from X-rays and ultraviolet to visible light. The X-ray variations, in particular, are often the most dramatic, as X-rays are typically produced in the hottest, innermost parts of the accretion disk closest to the black hole. The fact that the flickering is observed across this spectrum tells us that the entire inner accretion flow, the stream of gas and dust spiraling into the black hole, is somehow being affected. One proposed explanation for this flickering is that the black hole is feeding on small, discrete clumps of material rather than a smooth, continuous stream. Imagine dropping pebbles into a drain instead of pouring water. Each pebble would cause a temporary surge. Similarly, if the infalling gas and dust around the whirlpool's black hole is clumpy, each time a particularly dense clump falls into the innermost part of the accretion disk and is rapidly consumed, it could cause a temporary surge in luminosity observed as a flicker. The smaller the clumps and the faster they are consumed, the more rapid the flickering would be. This scenario suggests the accretion flow onto the whirlpool's black hole is turbulent and uneven, not the smooth laminar flow that is sometimes assumed in simpler models. The ongoing interaction with the companion galaxy could potentially contribute to creating this clumpiness in the gas supply, as tidal forces stir up and compress the interstellar medium in the galactic core. Another possibility involves instabilities within the accretion disk itself. Accretion disks are incredibly complex environments, with gas and dust orbiting at enormous speeds under the influence of strong gravity and powerful magnetic fields. These disks can be prone to various types of instabilities, which can cause parts of the disk to suddenly brighten or dim. Disk instabilities could manifest as temporary surges in mass accretion rate onto the black hole, or as changes in the structure or temperature of the disk, leading to observable variations in brightness. Magnetic fields are thought to play a crucial role in the behavior of accretion disks, driving turbulence and transporting angular momentum, which allows material to spiral inwards. Complex and rapidly changing magnetic field configurations near the black hole could potentially lead to sudden releases of energy or changes in the rate at which material falls onto the black hole, resulting in the observed flickering. Think of tangling and untangling a ball of string very quickly. The process can be chaotic and unpredictable. Magnetic fields around black holes can behave in similarly complex ways. Furthermore, the unusual tilted jet emanating from the whirlpool's black hole might also be playing a role in the flickering. The jet is powered by the accretion disk and the black hole's spin, and its orientation relative to the disk could influence the stability and behavior of the innermost accretion flow. If the jet's base is interacting with the inner disk in a complicated way due to its tilt, it could be causing temporary disruptions or changes in the flow of material onto the black hole, leading to the observed brightness variations. It's a complex feedback loop where the jet influences the disk and the disk powers the jet. The flickering might be providing us with clues about the intricate relationship between the black hole, its accretion disk, and the launching of these powerful jets. Studying the timing and characteristics of the flickering across different wavelengths can help astronomers disentangle these possibilities. Different processes like clump accretion, disk instabilities, or jet-disk interactions might leave distinct signatures in the pattern of the brightness variations. The persistent flickering of the Whirlpool's active nucleus is a vivid reminder that the centers of galaxies are incredibly dynamic and chaotic places, where the fundamental processes of black hole feeding and energy output are still not fully understood. It challenges us to develop more sophisticated models and gather even more detailed observations to unlock the secrets of these powerful cosmic engines. Adding to the Whirlpool Galaxy's complex structure is a subtle yet fascinating feature known as a polar ring illusion. While not a perfect, fully formed polar ring like those seen in truly spectacular examples, observations suggest the presence of a ring-like structure of gas and stars orbiting perpendicular or nearly perpendicular to the main galactic disk. Imagine a hula hoop spinning around someone's waist, and then another hula hoop spinning around their shoulders at a 90-degree angle. That's the kind of relationship between the main disk and a polar ring. In the case of the Whirlpool, this feature isn't as prominent as in classic polar ring galaxies, but the evidence points strongly towards it being there. This unusual orientation immediately tells us that this material didn't form in situ within the Whirlpool's original disk. The gas and stars in spiral galaxies typically settle into a flat disk due to the conservation of angular momentum, all orbiting in roughly the same plane. Material orbiting perpendicular to this plane must have come from somewhere else and been captured by the galaxy's gravity with a completely different orbital trajectory. The most widely accepted explanation for the formation of polar rings, and thus for the feature observed in the Whirlpool, is the tidal stripping and accretion of material from a smaller, gas-rich galaxy that was cannibalized by the larger galaxy. As a smaller galaxy is drawn in by the gravitational pull of a larger one, tidal forces can rip apart the smaller galaxy, pulling out streams of gas, dust, and stars. If this smaller galaxy is captured with an orbit that is significantly inclined relative to the plane of the larger galaxy's disk, perhaps coming in at a steep angle rather than along the same orbital path, the stripped material can settle into a ring-like structure that orbits around the larger galaxy at a high angle to its main disk. The gas, being able to dissipate energy more easily through collisions, can settle into a more stable, ring-like structure over time, while the stars might remain in a more diffuse halo. The Whirlpool's ongoing interaction with NGC 5195 makes this scenario particularly plausible. While NGC 5195 is still a distinct galaxy, it has already experienced significant tidal stripping, and the material pulled from it could be contributing to structures orbiting outside the Whirlpool's main disk. Perhaps the polar ring illusion is a remnant of an even earlier, more complete cannibalization event, or it could be material currently being stripped from NGC 5195 that is settling into a preferred orbital plane perpendicular to the Whirlpool's disk. The reason it's often referred to as a polar ring illusion in the case of M51 is that the feature isn't as clean and well-defined as in the most striking examples of polar ring galaxies, such as NGC 4650 or the Hoag's object. In these classic examples, the polar ring is a clearly visible, often bright, structure of gas, dust, and young stars that forms a prominent ring encircling the main galaxy. The polar feature in the Whirlpool is more subtle, perhaps less dense, more clumpy, or not yet fully settled into a perfect ring shape. It might be more of a complex network of filaments and streams of gas orbiting at high inclination, which, when viewed from our perspective, gives the appearance of a partial or irregular ring. Detecting and mapping this structure requires observations in wavelengths sensitive to cool gas, like radio waves, specifically the emission from neutral hydrogen, as well as infrared light, which can penetrate the dust and reveal the underlying stellar populations or gas distribution. Observations have revealed a significant amount of gas orbiting the whirlpool outside its main disk, with velocities that are inconsistent with rotation in the disk plane, supporting the idea of a highly inclined component. Comparing the whirlpool's polar feature to other known polar ring galaxies provides valuable context. Polar ring galaxies are relatively rare, making up only a small percentage of known galaxies, which suggests that the specific conditions required for their formation, including the type of interaction and the orbital geometry of the captured galaxy, are not common. Studying the variations in polar ring structures, from the prominent rings in classic examples to the more tenuous feature in the whirlpool, helps astronomers understand the range of outcomes from galaxy mergers and accretion events. It highlights that the process of building up galaxies through cannibalism is complex and can result in a variety of fascinating and sometimes ephemeral structures. The polar ring illusion in the whirlpool is a subtle but significant clue about its formation history, whispering of past encounters and the violent processes that have shaped this grand design spiral into the galaxy we observe today. It's a reminder that even seemingly secondary features can hold key information about a galaxy's evolution and its interactions with its cosmic neighbors. Beyond the light we see and the X-rays from hot gas, the Whirlpool Galaxy is also alive with invisible forces, colossal magnetic fields that weave through its spiral arms and halo, detected by sophisticated radio telescopes. These aren't like the magnets on your refrigerator. These are vast, galaxy-spanning fields, billions of times weaker than a fridge magnet but extending over immense distances, guiding the flow of charged particles and influencing the structure of the interstellar medium. What's particularly strange about the whirlpool's magnetic fields is their intricate and sometimes chaotic patterns. While spiral galaxies often have magnetic fields that generally align with their spiral arms, the whirlpool's fields show complex twists, turns, and even reversals in direction, especially in regions affected by the interaction with its companion galaxy. It's like observing a complex tapestry with threads that are not only following the main pattern, but also knotted and pulled in different directions in certain areas. Mapping these magnetic fields requires observing the polarized radio emission from the galaxy, which is light waves whose oscillations are aligned in a specific direction. The direction of this polarization is related to the direction of the magnetic field. By carefully measuring the polarization of radio waves coming from different parts of the whirlpool, astronomers can piece together a map of its vast magnetic architecture. These magnetic fields are not just a curious phenomenon, they are thought to play a crucial role in galactic processes, and their peculiar patterns in the whirlpool could be revealing hidden aspects of its dynamics. One key way magnetic fields influence galaxies is by guiding the flow of gas. Interstellar gas contains charged particles, and these particles tend to move along magnetic field lines like beads on a wire. In regions with strong and well-ordered magnetic fields, gas might be channeled along specific paths, potentially influencing how quickly it accumulates and collapses to form new stars. The tangled and distorted magnetic fields in the whirlpool, particularly where the spiral arms are most affected by the companion galaxy's gravity, could be either promoting or inhibiting star formation in different areas. Where magnetic fields are compressed and aligned, they might help channel gas into dense clouds, fostering star birth. Conversely, where the fields are highly turbulent, they might act to resist gravitational collapse, slowing down the process. The patterns in the magnetic field map could therefore be providing us with a blueprint of how gas is flowing through the galaxy, and how that flow is being influenced by the galactic interaction, ultimately affecting where and how stars are born. Another intriguing possibility is that the complex magnetic field patterns are directly revealing hidden gas flows that are otherwise difficult to detect. Gas in space isn't always hot enough to emit visible light or X-rays, but if it contains charged particles and is moving through a magnetic field, it can generate radio emission. The tangled magnetic fields in the whirlpool might be signatures of gas being pulled out of the main disk or sloshing around due to the gravitational disturbance from NGC 5195. Imagine stirring a bowl of soup with a magnetic whisk. If there were magnetic particles in the soup, they would follow the whisk's motion, revealing the complex flow patterns in the liquid. Similarly, the magnetic field patterns could be tracing the turbulent motion of charged particles embedded in the gas as it responds to the gravitational dance of the two galaxies. By comparing the magnetic field maps with observations of gas distribution and velocity, astronomers can look for correlations that might reveal these hidden flows. Furthermore, the magnetic fields themselves are likely being amplified and shaped by the violent processes occurring within the whirlpool. Supernova explosions and the turbulent motion of gas in the spiral arms and around the central black hole can generate and strengthen magnetic fields through a process called a galactic dynamo. The ongoing interaction with the companion galaxy likely enhances this dynamo effect, as the compression and stirring of the interstellar medium provide the energy needed to amplify the fields. The peculiar patterns we observe could be a snapshot of this dynamic process of magnetic field generation and amplification in an interacting galactic system. Studying the strength and structure of these fields provides valuable insights into the physical conditions within the galaxy, including the turbulence of the gas and the rate at which magnetic energy is being generated. The whispering magnetic fields of the Whirlpool Galaxy, detected through the subtle polarization of radio waves, are a powerful reminder that galaxies are permeated by these invisible forces which play a critical, though often hidden, role in shaping their structure, guiding their gas flows, and influencing the birth of stars. They add another layer to the galaxy's complexity, hinting at powerful dynamics that are not always visible in other wavelengths of light and pushing the boundaries of our understanding of cosmic magnetism. Stepping back away from the swirling arms and the chaotic core, the Whirlpool Galaxy reveals yet another layer of its enigmatic nature when viewed not in visible light but in infrared. What emerges is a massive, diffuse halo of cool dust, a vast ethereal cloud that stretches far beyond the galaxy's visible boundaries. In visible light, this dust is mostly opaque, blocking the light from stars behind it, but in infrared, which detects heat radiated by cooler objects, this hidden component of the galaxy glows faintly. This infrared halo is not made of the same hot gas found in the X-ray halo. This is much cooler material, existing at temperatures just tens or hundreds of degrees above absolute zero. Its sheer size and the amount of material it contains, potentially billions of solar masses worth of dust, are astonishing, and its presence so far from the main galactic disk poses a fascinating puzzle about its origin and role in the galaxy's evolution. Unlike the relatively warm dust associated with active star formation in the spiral arms, the dust in this halo is cold, suggesting it's not being heated by nearby young stars. So, where did all this dust come from? One compelling explanation ties the infrared dust halo to the cumulative effects of star formation within the Whirlpool Galaxy over cosmic timescales. As stars are born, live, and die, they process interstellar gas and dust. When massive stars end their lives as supernova, they not only blast out heavy elements but also create and disperse significant amounts of dust into the interstellar medium. Even lower mass stars, as they evolve into red giants and shed their outer layers, contribute to the dust content of a galaxy. Over billions of years, the continuous cycle of star birth and death within the whirlpool would have produced vast quantities of dust. While some of this dust remains in the galactic disk, involved in ongoing star formation, powerful outflows of gas driven by supernova and galactic winds could have expelled a significant portion of it into the galaxy's halo. Think of it like smoke rising from a factory. Gradually, the smoke disperses into the surrounding air. Similarly, dust created in the galactic disk could be lofted into the halo by energetic processes. In this scenario, the infrared dust halo is a vast repository of material recycled from countless generations of stars, a silent testament to the galaxy's long and active stellar history. The cool temperature of the dust in the halo suggests that it has been there for a significant amount of time, far from the heating influence of the galactic disk star-forming regions. Another intriguing possibility, particularly relevant given the Whirlpool's interactive nature, is that the infrared dust halo is composed of material that has been tidally stripped from either the Whirlpool itself or its companion galaxy, NGC 5195. As galaxies interact, their gravitational pulls can stretch and distort each other, ripping out streams of gas, dust, and stars. We've already seen evidence of tidal stripping in the warped dust lanes and potentially in the detached hydrogen cloud and blue outlier star clusters. It's plausible that a significant amount of dust, being less tightly bound by gravity than stars, has also been pulled out of the main galactic disks by the strong tidal forces during close encounters. This stripped dust, flung out into the space surrounding the galaxies, could then settle into a diffuse halo, held loosely by the combined gravitational pull of the Whirlpool companion system. The irregularity and clumpiness of some observed infrared halos around other galaxies support the idea that they can be formed from tidally disrupted material. Studying the motion of the dust within the Whirlpool's infrared halo, if possible, could provide clues about its origin. For example, if it shows velocity patterns consistent with being pulled from one of the interacting galaxies. The composition of the dust, if it can be determined from its infrared spectrum, might also offer hints. If the dust has a chemical signature similar to that found in NGC 5195, it would strengthen the case for tidal stripping from the companion. Furthermore, the infrared dust halo could also represent material that has been accreted from the intergalactic medium or from previously captured satellite galaxies that have now been completely dispersed. Galaxies are not isolated entities. They exist within a cosmic web of gas and dark matter, and they can draw in material from their surroundings over time. If the Whirlpool has accreted significant amounts of gas and dust from the intergalactic medium or from smaller galaxies that it has consumed, this material could contribute to the formation of a diffuse halo. This accreted material might have different properties or orbital histories compared to the material that formed the galaxy's disk, leading to its presence in the halo. Distinguishing between these different scenarios, dust expelled by supernova, tidally stripped material, or accreted gas and dust is challenging and likely requires a combination of observations in different wavelengths and sophisticated computer simulations that model the galaxy's evolutionary history. The sheer extent and mass of the infrared dust halo in the Whirlpool Galaxy highlight the fact that galaxies are surrounded by complex and often hidden structures of gas and dust, which play a significant role in their long-term evolution and their interactions with their environment. This cool, invisible halo is a fascinating phenomenon, revealing a vast reservoir of material that is a crucial component of the galaxy system, even though it is not readily apparent in the familiar visible light images. It reminds us that our view of galaxies is incomplete without looking at them through the lens of different parts of the electromagnetic spectrum. The drama of the Whirlpool Galaxy isn't limited to its own structure. It's also deeply intertwined with the fates of its companions, most notably the smaller, irregularly shaped galaxy NGC 5195, which gives the system its commonly used name M51A, signifying it's part of a pair. But the story gets even more complex as observations suggest a third, even smaller galaxy may also be involved in this cosmic ballet, a gravitational passe-deux-trois that's twisting and distorting the shapes of all participants. It's not just a two-body problem, It's a multi-body interaction where the gravitational forces are constantly shifting and pulling, fundamentally reshaping these galaxies. The most evident consequence of this interaction is the striking bridge of stars, gas, and dust connecting the Whirlpool Galaxy to NGC 5195, a cosmic hand extended between the two. This bridge is visual proof of the tidal forces at play, material being pulled out of both galaxies by their mutual gravitational attraction. Imagine stretching a piece of taffy between your hands. As you pull, a strand forms between the two main pieces. That's what's happening with the material connecting M51 and NGC 5195, a tangible link forged by gravity. The distortion isn't confined to the bridge. The very shapes of the galaxies are being warped. While the whirlpool retains its grand spiral form, its arms are clearly perturbed, stretched, and compressed in ways that wouldn't happen in isolation. The companion galaxy, NGC 5195, being smaller and less massive, is even more dramatically affected. It has lost much of its regular structure and appears as a distorted blob, its stars and gas feeling the stronger pull of the larger whirlpool. It's like a heavyweight boxer taking on a much lighter opponent. The heavyweight might be slightly jostled, but the lighter boxer is thrown around the ring. NGC 5195 is being physically pulled apart by the whirlpool, its outer regions particularly vulnerable to the tidal forces. This distortion is a continuous process, evolving over millions of years as the galaxies complete their orbital passes around each other. Each close approach strengthens the tidal forces, further reshaping the galaxies and drawing out more material. By measuring the velocities of stars and gas in both galaxies, astronomers can map out this gravitational dance and understand how the forces are distributed and affecting different parts of the system. These velocity maps show clear deviations from the smooth rotation expected in isolated galaxies, revealing the complex patterns of motion induced by the interaction. The potential involvement of a third, even smaller galaxy adds another layer of complexity to this gravitational dance. While this hypothetical third galaxy is much fainter and harder to detect, its gravitational presence, however small, could be influencing the dynamics of the M51 and NGC 5195 interaction. Even a small amount of extra mass in the vicinity, following a different orbital path, could subtly alter the gravitational field and affect how the two main galaxies interact. Perhaps this third galaxy is a dwarf galaxy that is also being tidally stripped by the whirlpool, or it could even be the remnant of a galaxy that merged with either M51 or NGC 5195 in the more recent past, its core having settled but its outer material still influencing the dynamics. Its gravitational pull, though weaker than that between the two main galaxies, could be enough to perturb their orbits or the flow of material between them, contributing to the overall distortion and the complex features observed in the system. Identifying and confirming the presence of this third galaxy is challenging, requiring sensitive observations that can detect its faint light and measure its motion. Astronomers search for overdensities of stars, streams of gas, or even slight anomalies in the gravitational field that could point to its existence. The dancing companion galaxies in the M51 system and the potential for a third partner provide us with a unique laboratory to study the mechanics of galactic interactions in real time, relatively speaking. We are witnessing a gravitational ballet that has been ongoing for hundreds of millions of years and will continue for millions more. Understanding how their mutual gravity is distorting their shapes, pulling out material, and potentially triggering star formation is crucial for understanding how galaxies evolve and grow. Galactic interactions are a fundamental process in the universe, driving the formation of larger structures and influencing the properties of the galaxies involved. The M51 system is a prime example of this process, offering a complex and dynamic scenario where multiple galaxies are engaged in a gravitational dance that is shaping their past, present, and future. Each twist and turn in their shapes, each stream of material pulled free, is a consequence of this ongoing interaction, a testament to the powerful and transformative force of gravity on a cosmic scale. Focusing our attention on that cosmic bridge connecting the Whirlpool Galaxy and its smaller companion, NGC 5195, we see more than just stretched out stars and dust. Embedded within this tidal bridge are delicate, luminous filaments of gas glowing brightly enough to stand out in astronomical images. These aren't just passive streams of material. They are evidence of energized gas, material that is being heated and excited by powerful forces at play within the bridge. Imagine taking those threads of taffy and running an electric current through them, causing them to glow faintly. That's a simplified analogy for what might be happening with these gas filaments. Their brightness suggests they are emitting light, likely because the gas within them is either very hot or being bombarded by high-energy particles. The fact that they form these long, stringy structures extending between the two galaxies is a strong indication that their existence is intimately linked to the ongoing interaction. What could be causing this gas to glow so brightly in these specific filamentary patterns? One primary explanation for the luminosity of these gas filaments is that they trace the paths of powerful shock waves generated by the galactic collision. When two galaxies interact, even in a glancing or indirect way like the Whirlpool system, the immense clouds of gas within them collide at high speeds. These collisions create shock waves, similar in principle to a sonic boom produced by a jet breaking the sound barrier, but on a vastly larger and more energetic scale. As these shock waves propagate through the gas in the tidal bridge, they compress and heat the gas to high temperatures, causing it to emit light. The gas can also glow as high-energy particles, accelerated by the shock waves, collide with atoms in the gas and excite their electrons, which then release photons as they return to their ground state. The filamentary structure of the glowing gas suggests that the shock waves are not uniform across the bridge but are localized, perhaps propagating along specific channels or encountering denser clumps of gas in certain areas. These glowing tendrils are essentially highlighting the regions within the bridge where the gas is experiencing the most violent consequences of the galactic collision, acting as cosmic tracers of the energy being dissipated through shock heating. Studying the spectrum of the light emitted by these filaments can reveal the temperature and density of the gas, as well as the presence of different elements, providing valuable information about the physical conditions within the shock waves. Different elements emit light at specific wavelengths when heated or excited, leaving unique fingerprints in the light spectrum. Another factor contributing to the luminosity of these filaments could be intense star formation triggered within the tidal bridge itself. Tidal bridges formed from gas stripped out of interacting galaxies can become dense enough in certain regions for gravity to overcome the internal pressure of the gas, leading to the collapse of clouds and the birth of new stars. If star formation is occurring within these filaments, the intense ultraviolet light from newly formed massive stars would ionize the surrounding hydrogen gas, causing it to glow with a characteristic reddish color hydrogen alpha emission, similar to what we see in star-forming regions within galactic disks. The presence of young star clusters within the tidal bridge, which has been observed in other interacting systems, would further support this idea. However, the specific colors and spectra of the glowing filaments in the Whirlpool's bridge need to be carefully analyzed to determine the dominant source of their luminosity. If the glow is primarily due to shock heating, the spectrum might show emission lines from elements in different ionization states, indicating very high temperatures. If it's driven by star formation, the spectrum might be dominated by emission lines characteristic of ionized hydrogen and other elements commonly found in stellar nurseries. It's possible, of course, that both shock heating and star formation are contributing to the glow, with different processes dominating in different parts of the filaments. Furthermore, the powerful magnetic fields we discussed earlier likely play a role in shaping and confining these glowing gas filaments. As charged particles in the hot gas move through the magnetic fields in the tidal bridge, their motion is constrained by the field lines. This can cause the gas to flow and accumulate along specific magnetic pathways, forming the observed filamentary structures. The magnetic fields might also be amplified within the shock waves themselves, further contributing to the structure and energy of the glowing gas. The tangled and distorted magnetic fields detected in the Whirlpool system are likely interacting with the gas in the tidal bridge in complex ways, guiding the shock waves and channeling the flow of energized material. The glowing gas filaments are therefore not just a consequence of gas being stretched between the galaxies. They are a product of the violent interplay between gravity, gas dynamics, and magnetic fields in the chaotic environment of a galactic collision. Their very existence and structure are a powerful visual representation of the energy and forces at work in shaping interacting galaxies and the bridges of material that connect them, offering a tangible glimpse into the destructive and creative power of cosmic encounters. Despite having a supermassive black hole at its heart and engaging in a dramatic cosmic dance with a companion galaxy, the Whirlpool Galaxy presents another paradox. Its nucleus, while active, is surprisingly dim for a galaxy undergoing such turbulence. We've talked about the flickering, the jets, and the twin nuclei possibility, but all of this activity seems muted compared to what astronomers might expect from a galaxy in the throes of interaction. Galaxies with actively feeding supermassive black holes are often classified as quasars or Seyfert galaxies, which are known for their exceptionally bright nuclei, outshining even the combined light of all the stars in the host galaxy. The Whirlpool's nucleus, while showing signs of activity, is nowhere near that level of brilliance. It's like finding a powerful engine that's only running at a fraction of its capacity. This relative faintness has led some astronomers to describe the Whirlpool's core as a quiet quasar, a term that captures the strange disconnect between the potential for extreme energy output and the observed, comparatively subdued luminosity. The question is, why is this supermassive black hole, located in such a dynamic environment, not shining more brightly? One compelling explanation for the Whirlpool's quiet nucleus is that the supermassive black hole at its center is currently in a relatively dormant phase. Black holes don't feed constantly. Their activity levels can wax and wane depending on the availability of gas and dust in their immediate surroundings. If there isn't a large, steady supply of material spiraling into the black hole's accretion disk at the moment, the energy output from the core would be significantly reduced. While the galactic interaction is stirring up gas and dust throughout the galaxy, it's possible that this material hasn't yet reached the very center in sufficient quantities to fuel a fully fledged quasar-like outburst. The infall of gas onto a supermassive black hole is a complex process, and there can be bottlenecks or barriers that prevent the material from reaching the innermost regions where the most intense radiation is produced. Perhaps the current configuration of gas flows in the Whirlpool's core is such that the black hole is only receiving a trickle of material compared to what it could potentially consume. In this scenario, the observed activity, like the flickering and the jet, would be powered by these smaller, intermittent infall events, not a sustained, high-rate accretion that would drive a bright quasar phase. It's like a furnace that's only being fed a small amount of fuel at a time, producing some heat and sparks but not reaching its full roaring potential. Another significant factor that could explain the seemingly dim nucleus is simply obscuration by vast amounts of dust and gas located between the black hole and our telescopes. The core of a galaxy is often a very dusty and gas-rich environment, particularly in galaxies undergoing interactions that compress and concentrate interstellar material. Dust is incredibly effective at absorbing and scattering light, especially at shorter wavelengths like visible light and X-rays. If the central black hole and its accretion disk are surrounded by a thick torus or curtain of dust, much of the light and radiation they produce could be blocked from reaching our line of sight. We might only be seeing a fraction of the true luminosity of the core, with the rest being hidden behind this opaque screen. Imagine trying to see a bright light bulb through a thick fog. It would appear much dimmer than it actually is. This dust obscuration is a common phenomenon in active galaxies, and in some cases it can completely hide the central engine in visible light, making it appear as a quiet galaxy even if the black hole is actively feeding. Infrared and radio observations, which can penetrate dust more effectively than visible light and X-rays, are often used to look for signs of heavily obscured active galactic nuclei. If the Whirlpool's core appears brighter in infrared or radio wavelengths than expected based on its visible light luminosity, it would provide strong evidence for dust obscuration being a major factor in its apparent dimness. The tilted jet from the black hole, which we discussed earlier, might also play a role in the observed dimness if it's not pointed directly towards us. While the jet itself is a source of high-energy emission, its appearance and apparent brightness depend on the angle from which we view it. If the jet is tilted significantly away from our line of sight, its emission might be beamed in a different direction, making the core appear less luminous to us even if the jet is intrinsically powerful. However, the jet is only one component of the active nucleus. The accretion disk itself is a major source of light and X-rays, and its emission is generally more isotropic, meaning it's radiated more or less equally in all directions, aside from potential shadowing by the torus. Therefore, while the jet angle could contribute, it's unlikely to be the sole explanation for the overall dimness unless the jet is extremely dominant in powering the observed luminosity, which is often not the case in Seyfert-like nuclei. The most likely culprits for the Whirlpool's quiet quasar status are a combination of a currently lower accretion rate onto the black hole and significant obscuration by dust and gas in the galactic core. Distinguishing between how much of the dimness is due to a truly dormant phase versus how much is due to dust obscuration requires careful analysis of observations across the entire electromagnetic spectrum, looking for signatures of activity that might be hidden in visible light. The mystery of the quiet quasar in the Whirlpool Galaxy's core highlights the complex and sometimes hidden nature of supermassive black holes and their powerful influence on their host galaxies. It reminds us that not all active nuclei display their full brilliance, and that understanding their true nature requires peering through the cosmic veils of dust and considering the dynamic interplay between the black hole and its ever-changing environment. Look closely at the spiral arms of the Whirlpool Galaxy and compare them to the distorted structure of its companion, NGC 5195, and you might notice something truly uncanny, a striking similarity in the locations and appearances of their star-forming regions. It's almost as if these stellar nurseries are mirroring each other across the vast expanse between the two galaxies, a synchronized burst of stellar creation occurring in corresponding areas. In M51, you see bright knots of gas and dust glowing with a telltale pinkish red of ionized hydrogen, marking where new stars are being born. Look across the cosmic bridge to NGC 5195, and you find similar bright knots located in positions that seem to reflect the pattern in its larger partner. This isn't likely a random coincidence. The mirroring suggests that the ongoing gravitational interaction between the two galaxies is not only distorting their shapes but also triggering star formation in a coordinated fashion, a cosmic duet where stellar births are happening in sync. This synchronized star formation points strongly towards shared triggering mechanisms, forces that are simultaneously affecting both galaxies and prompting gas clouds to collapse and ignite new stars. One leading candidate for this synchronized trigger is the passage of shock waves through the interstellar medium of both galaxies. As the galaxies pass close to each other, their gravitational interaction creates tidal forces that compress and stir up the gas and dust in their disks. These compressions can propagate as shock waves, traveling through the galactic material like ripples on a pond. When these shock waves encounter dense gas clouds, they can provide the extra push needed to overcome the cloud's internal pressure and trigger gravitational collapse, leading to star formation. The mirroring of the star-forming regions suggests that the shock waves are traveling outwards from the points of closest gravitational influence and are affecting both galaxies in similar ways at similar times. Imagine throwing two stones simultaneously into a pond. The ripples would spread outwards from both points of impact, and if you had objects floating on the surface, those caught by corresponding ripples might behave similarly. On a galactic scale, the gravitational disturbance from the interaction acts like those stones, sending shock waves that are triggering star formation in mirroring patterns within the gas disks of both M51 and NGC 5195. Studying the distribution and velocities of the gas in both galaxies provides evidence for these shock waves, revealing regions where the gas is being compressed and heated. Another possibility contributing to this mirroring is the shared supply of gas that is being pulled and redistributed by the interaction. The tidal bridge connecting the two galaxies is made up of materials stripped from both. This shared pool of gas and dust is being funneled and concentrated in certain areas due to the complex gravitational forces of the interaction. If this material is being channeled into specific regions in both galaxies in a coordinated way, those regions would become denser and more likely to form stars. Think of two sinks connected by a pipe. If you pour water into the pipe, it will flow into both sinks simultaneously. Similarly, the tidal forces are effectively creating shared channels through which gas is flowing and accumulating in corresponding areas within the two galaxies, leading to enhanced star formation in those locations. The distribution of gas within the tidal bridge and its connection to the star-forming regions in both galaxies are crucial areas of study for astronomers trying to confirm this scenario. Observing the density and motion of the gas in the bridge using radio telescopes that detect cool hydrogen is key to understanding how material is being transported and triggering star formation in both galaxies. Furthermore, the interplay of magnetic fields, which are also being affected by the galactic interaction, could contribute to channeling gas and triggering star formation in these mirroring regions. Magnetic fields can act like invisible scaffolding, guiding the flow of charged particles and influencing the behavior of gas clouds. If the magnetic fields in the interacting system are being compressed and aligned in a way that mirrors the gravitational forces, they could be directing gas flows into specific, corresponding regions in both galaxies, further enhancing the synchronized star formation. The complex magnetic field patterns we discussed earlier, particularly in the regions affected by the interaction, are therefore likely intimately connected to the observed mirroring of star-forming activity. The very act of two galaxies colliding doesn't just shuffle existing stars, it actively rewrites the conditions for creating new ones, and in the Whirlpool system, this process appears to be happening in a strangely synchronized, almost mirrored fashion. This phenomenon highlights the intricate and sometimes surprising ways in which galactic interactions can reshape not just the large-scale structure of galaxies, but also the fundamental process of stellar birth within them, creating patterns of creation that reflect the gravitational dance they are performing. Stepping even further back into the Whirlpool Galaxy's history, we encounter a puzzling scarcity that hints at dramatic events in its past, the surprisingly low number of ancient globular clusters surrounding it. Globular clusters are dense, spherical collections of hundreds of thousands to millions of stars, typically very old, forming some of the earliest structures in a galaxy's history. They are like fossil records containing stars that formed billions of years ago and have remained gravitationally bound ever since. Most large galaxies like the Whirlpool are expected to host hundreds, sometimes even thousands, of these ancient stellar relics orbiting in their halos. Our own Milky Way, for instance, has over 150 known globular clusters, but observations suggest the Whirlpool Galaxy has significantly fewer than expected for a galaxy of its size and type, a cosmic mystery that raises questions about its formation and evolutionary path. Where are the missing globular clusters? Their absence is a strong anomaly, pointing towards processes that have either prevented their formation or, more likely, destroyed them over cosmic time. One compelling theory for the missing globular clusters is tidal destruction. We've already seen how the gravitational interaction with NGC 5195 is distorting the whirlpool structure and pulling out streams of material. While this current interaction is significant, it's possible the whirlpool has experienced closer or more violent encounters with other galaxies in the past. When a dense star cluster, like a globular cluster, passes close to the center of a much larger galaxy or experiences strong tidal forces from an interacting companion, its outer stars can be stripped away by gravity. Imagine a swarm of bees flying too close to a powerful magnet. The outer bees would be pulled away from the main group. Similarly, the tidal forces can pull stars away from the outer regions of a globular cluster. Over repeated close passes or during a particularly disruptive interaction, a globular cluster can be gradually dismantled, its stars dispersed into the galactic halo, eventually becoming indistinguishable from the general background stellar population. If the whirlpool has undergone several significant tidal interactions or has a particularly strong central gravitational pull, it could have tidally disrupted a large fraction of its original globular cluster population. The missing clusters could be the remnants of these disrupted systems, their stars now scattered throughout the whirlpool's halo, a ghostly, invisible memorial to their former glory. Another, perhaps even more dramatic, explanation for the low number of globular clusters points to a very active, merger-heavy past for the Whirlpool Galaxy. Galaxies grow and evolve by merging with other galaxies, both large and small. Major mergers where two galaxies of roughly equal size collide are incredibly violent events. When galaxies merge, their cores can pass through each other multiple times, and the powerful gravitational forces involved can scatter stars, gas, and star clusters into the surrounding space. While some globular clusters might survive a merger relatively intact, many others can be destroyed or significantly disrupted by the tidal forces and the chaotic gravitational field. Furthermore, the intense star formation triggered by a major merger can sweep through the galaxy, and the resulting supernova explosions and galactic winds can also contribute to the destruction of older stellar systems. If the Whirlpool Galaxy was formed or significantly grew through one or more major mergers in its history, it could have lost a substantial portion of its ancient globular cluster population in the process. The low number of clusters we observe today would therefore be a direct consequence of a violent, merger-driven formation history. This scenario is supported by some simulations of galaxy formation, which show that galaxies that have undergone more major mergers tend to have fewer surviving globular clusters compared to galaxies with quieter evolutionary paths. The relative scarcity of globular clusters in the whirlpool also raises questions about the initial conditions in the region of space where it formed. Perhaps the conditions in the early universe in that particular volume of space were not as conducive to the formation of large, dense globular clusters as in other regions. However, this is a less favored explanation, as globular clusters are thought to be a common and ancient component of most large galaxies. The most likely explanations tie the missing clusters to the galaxy's dynamic and potentially violent history. Studying the properties of the few globular clusters that the whirlpool does possess, such as their ages, chemical compositions, and orbital paths, can provide valuable clues. If the remaining clusters show signs of tidal disruption or have unusual orbits, it would strengthen the case for destruction by tidal forces or past mergers. Similarly, comparing the star formation history inferred from the whirlpool stars with theoretical models of galaxy evolution through mergers can help determine if a merger-heavy past is consistent with the observed stellar populations and the low globular cluster count. The mystery of the vanishing globular clusters in the Whirlpool Galaxy is a powerful reminder that a galaxy's present appearance is deeply shaped by its past, often violent, history, and that even seemingly empty spaces around a galaxy can hold crucial clues about its tumultuous journey through cosmic time. Shifting our gaze from the fiery heart and stretching halo of the Whirlpool Galaxy, we notice something peculiar within its luminous spiral arms, regions that appear strangely dark when viewed in ultraviolet light. These aren't simply gaps between the arms, these are patches where the intense, high-energy light typically emitted by young, hot stars seems to be missing or significantly diminished, creating what astronomers have dubbed UV holes. Imagine looking at a brightly lit city at night but seeing occasional areas where the streetlights are out, leaving dark patches against the general glow. These UV holes in M51 are similar cosmic phenomena, hinting at hidden processes or structures that are interacting with or blocking the ultraviolet radiation. Ultraviolet light is primarily emitted by the hottest and most massive stars, those that are born in regions of active star formation and burn with incredible intensity for relatively short periods. Their presence is a strong indicator of recent or ongoing stellar birth. So, the absence of this light in specific patches within the Whirlpool's spiral arms is counterintuitive, especially since spiral arms are generally where star formation thrives. What could be causing these localized dips in ultraviolet brightness? The most straightforward explanation for the UV holes lies in the presence of remarkably dense clouds of gas and dust. While dust lanes are common in spiral galaxies and are the raw material for star formation, these dust clouds would have to be exceptionally thick and opaque in ultraviolet wavelengths to create such pronounced dark patches. Dust is particularly effective at absorbing and scattering ultraviolet light. If a young, hot star is embedded within or behind a very dense cloud of dust and gas, much of the ultraviolet light it emits would be absorbed or scattered away before it can escape the cloud and reach our telescopes. It's like a dense fog blocking sunlight. The fog particles absorb and scatter the light, making the area appear darker. The UV holes could therefore be highlighting regions within the Whirlpool's spiral arms where the interstellar medium is unusually dense, perhaps due to localized compression or turbulence. These dense clouds might be on the verge of collapsing to form new stars, or they could be regions of material that have been recently stirred up by the galactic interaction, becoming temporarily opaque to ultraviolet light. By observing these regions in other wavelengths, such as infrared or radio waves, which can penetrate dust more easily, astronomers can look for evidence of these dense clouds and see if they correlate with the location of the UV holes. Infrared emission from warm dust or radio emission from cool gas would confirm the presence of a significant amount of material in these dark patches. Another intriguing possibility for the UV holes is that they represent temporary lulls or gaps in star formation activity within those specific regions. While the Whirlpool Galaxy is experiencing enhanced star formation overall due to its interaction with its companion, this process isn't necessarily uniform across the entire galaxy. Star formation occurs in bursts, and the rate at which stars are born can vary significantly from one region to another. The UV holes could correspond to areas within the spiral arms where the conditions for star formation are temporarily unfavorable, perhaps due to lower gas density, weaker triggering mechanisms, or local feedback from previous stellar activity. For instance, powerful stellar winds from newly formed massive stars or shock waves from supernova explosions can sometimes disperse the surrounding gas and dust, temporarily shutting down further star formation in that immediate vicinity. If such feedback mechanisms have recently cleared out the gas from specific regions, those areas would lack the hot, young stars that are the primary source of ultraviolet light, leading to the appearance of a UV hole. It would be like a garden bed where planting has temporarily stopped after a harvest. While the surrounding areas might still be actively fertile, these specific spots are currently fallow. Distinguishing between dense dust obscuration and a genuine lull in star formation requires careful analysis of the stellar populations within the UV holes. If sensitive observations can detect older, less massive stars in these regions but a clear absence of very young, hot stars, it would support the idea of a star formation lull. Furthermore, the complex interplay of gas dynamics and gravitational forces driven by the galactic interaction could be creating transient conditions that lead to these UV holes. The warping and twisting of the spiral arms and dust lanes that we discussed earlier could be creating localized areas where the gas density is temporarily lower, or where the gas is being channeled away, making those regions less conducive to immediate star formation and thus reducing their ultraviolet output. The passage of a shock wave might compress gas ahead of it, triggering star formation, but leave a less dense region in its wake, creating a temporary UV dark patch. It's a dynamic, constantly changing environment, and the UV holes might be snapshots of these temporary fluctuations in gas density and star-forming conditions. The very pattern of these UV holes within the spiral arms, whether they are randomly distributed or follow specific structures, could provide clues about the underlying mechanisms at play. If they are aligned with specific features of the warped dust lanes or correspond to regions where gas is being pulled away, it would link their existence directly to the ongoing galactic interaction. The mysterious UV holes in the Whirlpool Galaxy are therefore not simply empty spaces. They are windows into the complex and dynamic processes of star formation and the interaction of light with the interstellar medium in a colliding galaxy. Their darkness speaks volumes about the hidden density of dust or the transient nature of stellar birth, adding another layer of intrigue to the already fascinating tapestry of the Whirlpool. Moving away from the current activity in the Whirlpool Galaxy, we glimpse something that speaks of a powerful event from centuries past, a strange, echoing light burst not from a present eruption, but from light bouncing off vast clouds of dust, creating expanding rings of light that we are only now seeing. Imagine dropping a pebble in a pond, the ripples spread outwards. In space, a powerful flash of light, like from a supernova explosion or a sudden burst from the central black hole, can act like that pebble. If there are clouds of interstellar dust surrounding the source, the light from the flash doesn't just travel directly towards us. Some of it is scattered by the dust particles, reflecting off the dust in different directions. As the light travels outwards and scatters off dust clouds at increasing distances from the source, and at slightly different angles, it reaches us over a period of time, not all at once. This creates the appearance of expanding rings or shells of light centered on the original source, an optical illusion known as a light echo. It's like seeing the flash from a distant firework reflected off layers of mist, each reflection reaching you a moment later than the one before. The fact that we are seeing this echoing light burst in the Whirlpool Galaxy, still visible as expanding rings, indicates that a powerful, impulsive event occurred there in the relatively recent past, perhaps within the last few hundred years, which is a blink of an eye in cosmic terms. The size and rate of expansion of the rings can tell astronomers about the distance to the dust clouds and the geometry of the surrounding interstellar medium. What kind of event could have produced a flash of light powerful enough to create such a long-lasting and extensive light echo in the Whirlpool Galaxy? One prime suspect is a supernova explosion that occurred centuries ago, whose light is now reaching us via reflection off intervening dust clouds. We know the Whirlpool experiences supernova. We've already discussed the two observed in recent decades. It's entirely plausible that another, perhaps even brighter, supernova occurred there several hundred years ago, its direct light having long since passed us by, but its scattered light continuing to arrive as it bounces off surrounding dust. The specific type of supernova would influence the characteristics of the light flash. A Type II supernova from the core collapse of a massive star, or a Type I a supernova from the explosion of a white dwarf, both produce incredibly luminous bursts of light. If the original explosion was particularly energetic and the surrounding dust distribution is just right, it could create a prominent and long-lived light echo. By carefully measuring the rate at which the light echo rings are expanding across the sky and knowing the distance to the Whirlpool Galaxy, astronomers can calculate the actual speed at which the light is traveling outwards and scattering off the dust. This speed should, of course, be the speed of light, confirming that it is indeed a light echo phenomenon. Furthermore, the spectrum of the light in the echo can sometimes reveal clues about the original source. Although the light is scattered, it retains some of the spectral characteristics of the initial flash, which could potentially allow astronomers to identify the type of event that caused it, for example, by showing the spectral lines typical of a supernova. Another potential culprit for the echoing light burst is a powerful, though perhaps temporary, outburst from the supermassive black hole at the center of the Whirlpool Galaxy. Black holes in the nuclei of galaxies aren't always quiet. They can undergo episodic bursts of activity where they rapidly accrete a large amount of material, producing a sudden and intense flare of radiation across the electromagnetic spectrum, including visible light and X-rays. These outbursts, while not as common as supernova, can be incredibly luminous. If the Whirlpool's central black hole had such an energetic flare centuries ago, its light could also be scattering off surrounding dust clouds in the galactic core, creating a light echo. The flickering behavior we discussed earlier, while on much shorter timescales, hints at the dynamic nature of the accretion process around the black hole, suggesting it is capable of undergoing sudden changes in luminosity. A more powerful version of these flickering events, a true outburst or flare, could certainly generate the necessary light to produce a detectable light echo. Distinguishing between a supernova and a black hole flare as the origin of the light echo can be challenging, but the location of the echo is a key clue. If the expanding rings are centered precisely on the galactic nucleus, it strongly favors the black hole as the source. If they are centered elsewhere, in the spiral arms for example, it points towards a supernova or another stellar event as the cause. The nature of the dust distribution is also critical. The structure and extent of the light echo are directly shaped by the density and geometry of the dust clouds surrounding the original light source. The detection and study of this echoing light burst in the Whirlpool Galaxy provides a unique way to probe both the history of energetic events within the galaxy and the distribution of interstellar dust in the regions around the source. It's a cosmic time capsule, allowing us to witness the reverberations of a powerful explosion that occurred long before our time, as its light continues its slow journey towards us, scattered and delayed by the dust that permeates the vast spaces within the galaxy. It's a silent, expanding testament to the violent and dynamic nature of cosmic phenomena. Adding another layer to the Whirlpool Galaxy's structural peculiarities is the discovery of a significant disk of cool gas that appears to be orbiting at a distinctly odd angle relative to the main disk of stars. We think of spiral galaxies as being relatively flat, with stars and gas orbiting in a common plane, much like the planets in our solar system orbit the Sun in roughly the same plane. But observations of the Whirlpool, particularly using radio telescopes that can detect the emission from cool atomic and molecular gas, have revealed a large amount of gas that isn't participating in this neat, ordered motion. Instead, it's orbiting the galactic center on a tilt, forming a second, smaller disk that is misaligned with the primary stellar disk. Imagine the hula hoop analogy again, not quite perpendicular, but definitely at a significant slant compared to the main one. This misaligned gas disk is a strong indicator that this gas didn't form as part of the original galaxy. It must have been acquired from elsewhere, bringing its own orbital momentum with it. Its presence tells a story of external influences and the chaotic process of galactic assembly. The most plausible explanation for the origin of this misaligned gas disk is the accretion of gas-rich material from a recent merger or interaction with another galaxy. Galaxies grow by merging with and consuming smaller galaxies, and if the captured galaxy was rich in gas and fell into the whirlpool on an inclined orbit, its gas could settle into a disk that is tilted relative to the whirlpool's pre-existing stellar disk. The gravitational forces from the larger galaxy would draw in the gas, and over time, the gas particles would collide and settle into a disk-like structure, but one that retains the orbital inclination of the incoming material. This scenario fits well with the whirlpool's known history of interaction and potential mergers. Perhaps the misaligned disk is composed of gas that was pulled from the companion galaxy NGC 5195 during a past close pass, or it could be the remnants of a different, gas-rich dwarf galaxy that was completely swallowed by the whirlpool in a relatively recent cosmic epoch. The gas in the misaligned disk would gradually lose energy through collisions and might eventually align with the main stellar disk over billions of years, but its current tilted state indicates it hasn't had enough time to fully settle in. The amount of gas in this misaligned disk is significant, suggesting the captured material was substantial. The velocities and distribution of the gas within this tilted disk can be mapped out using radio telescopes, providing crucial data points that astronomers can compare with computer simulations of galaxy mergers and gas accretion to see if they match the predictions for a captured gas disk. Another possibility is that the misaligned gas is not the result of a single, large merger, but is instead due to the ongoing accretion of gas from the intergalactic medium or from smaller clumps of satellites falling into the whirlpool's gravitational pull over an extended period. Galaxies are embedded within a cosmic web of gas, and they can draw in this diffuse material over time. If this accreted gas isn't approaching the galaxy along the same plane as its disk, but is instead falling in from various directions, it could settle into orbits that are misaligned with the main disk. The continuous accretion of gas with different angular momenta could build up a complex structure of gas flows and eventually settle into a tilted disk. The Whirlpool Galaxy, located in a region of decent cosmic density, could be continuously accreting gas from its environment. This accreted gas, if it's not perfectly aligned with the existing disk, would then contribute to the misaligned component. Evidence for this ongoing accretion can sometimes be seen as faint streams of gas or small clumps orbiting the galaxy in its outer halo. While less dramatic than a large merger, this continuous trickle of gas could, over time, build up a noticeable misaligned component if the incoming material has a consistent overall inclination. Distinguishing between a single, recent merger and ongoing accretion as the cause of the misaligned gas disk can be challenging. However, the overall structure and kinematics of the misaligned gas provide clues. A single merger might inject gas with a relatively coherent orbital direction, leading to a somewhat well-defined tilted disk. Ongoing accretion from the intergalactic medium might result in a more chaotic or clumpy distribution of misaligned gas. The chemical composition of the gas might also offer hints. If the misaligned gas has a different metallicity, the abundance of elements heavier than hydrogen and helium, compared to the gas in the whirlpool's main disk, it would support the idea that it originated from a different cosmic environment, like a less evolved dwarf galaxy or the more pristine gas of the intergalactic medium. The misaligned gas disk in the Whirlpool Galaxy is a powerful indicator of its dynamic history and its continuous interaction with its cosmic environment. It highlights that galaxies are not static entities but are constantly evolving, growing, and changing their structure through interactions and the accretion of new material. This tilted disk of gas is a visible scar of a past encounter or an ongoing process of cosmic nourishment, adding another fascinating layer to the whirlpool's already complex and intriguing nature. Right in the pulsating heart of the Whirlpool Galaxy, surrounding the supermassive black hole and the mystery of the twin nuclei, lies another peculiar feature, an incredibly dense concentration of stars, forming what astronomers have described as an overcrowded central star cluster. We expect to find a bulge of stars at the center of most spiral galaxies, a spheroid of older stars tightly packed together. But in the whirlpool, this central density is particularly extreme, with stars crammed into a relatively small volume, far more so than in the centers of many other galaxies of similar size. Imagine a bustling metropolis, but with every building significantly taller and closer together than you'd normally expect. That's the kind of stellar density we're talking about in M51's core. This isn't just a casual observation. Detailed studies of the light from the central region, analyzing the motion and distribution of stars, confirm this unusually high stellar density. The stars are orbiting the galactic center at very high speeds, held there by the immense combined gravitational pull of the supermassive black hole and the sheer mass of all the surrounding stars packed into such a tight space. Their close proximity to each other and to the central black hole creates an environment that is both fascinating and potentially hazardous for these stellar inhabitants. The sheer number of stars packed into the whirlpool's core immediately raises questions about how such a dense cluster formed and managed to survive in such a turbulent environment. One theory is that this overcrowded center is partly a consequence of the ongoing galactic interaction. As the companion galaxy, NGC 5195, passes close to the whirlpool, its gravitational pull stirs up gas and stars throughout the larger galaxy, particularly in the central regions. This gravitational stirring can cause stars from the outer bulge to lose orbital energy and spiral inwards towards the center, like marbles rolling down a funnel. Over millions of years of repeated close passes with the companion, this process of dynamical friction could have funneled a significant number of stars into the very core, increasing the stellar density to the extreme levels we observe. Furthermore, the compression of gas in the central regions, potentially triggered by the interaction, could have led to a burst of star formation right at the galaxy's heart in the past, adding a new population of stars to the pre-existing bulge and further increasing the density. This scenario links the unusual nature of the whirlpool's core directly to its current cosmic dance, suggesting that the interaction is actively building up the stellar density at the center. However, the survival chances of stars in such an overcrowded and dynamic environment are significantly different from those in the more sedate regions of a galaxy. In the galaxy's outer disk, stars are typically separated by vast distances, and close encounters are rare. But in the whirlpool's core, stars are so tightly packed that close gravitational interactions between individual stars are much more frequent. These encounters can disrupt stellar orbits, heat up the star cluster, and even lead to stellar collisions, although direct collisions are still relatively rare even in such dense environments. The most significant hazard, however, comes from the supermassive black hole that lies at the very heart of this overcrowded cluster. Any star that wanders too close to the black hole's event horizon risks being torn apart by its immense tidal forces, a process known as tidal disruption. The intense gravity stretches the star, pulling harder on the side facing the black hole than on the side facing away, until the star is ripped into a stream of gas, some of which is then accreted by the black hole, causing a temporary flare. The high density of stars in the whirlpool's core means that stars are more likely to have their orbits perturbed in a way that sends them on a trajectory towards the central black hole, increasing the rate of these tidal disruption events. It's a dangerous neighborhood for stars where gravitational nudges can have fatal consequences. Astronomers study the light signatures of these tidal disruption events, looking for characteristic flares of X-rays and ultraviolet light that occur when a star is shredded by a black hole. While such events are relatively rare in any single galaxy at any given time, a galaxy with an overcrowded core and an active supermassive black hole like the whirlpool is a prime candidate for hosting them. The sheer number of stars in close proximity to the black hole increases the statistical probability of a star wandering too close. The overcrowded center of the Whirlpool Galaxy therefore serves as a unique laboratory for studying the dynamics of stellar systems under extreme gravitational conditions and the interaction between stars and supermassive black holes. It raises intriguing questions about the long-term evolution of star clusters in galactic centers and the ultimate fate of stars that find themselves in such a perilous cosmic environment. Is this overcrowding a temporary state, or will the black hole eventually consume enough stars to thin out the central cluster? The unusual density of stars at the Whirlpool's heart is not just a curiosity. It's a key feature that links the galaxy's large-scale structure to the powerful processes happening in its core and provides a glimpse into the chaotic, sometimes destructive, interplay between stars and the supermassive black holes that dominate galactic centers. Moving outwards from the overcrowded core and the main, distorted spiral arms of the Whirlpool Galaxy, astronomers have detected faint, ethereal wisps of stars and gas that don't seem to fit neatly into the galaxy's grand design. These are not part of the main, bright spiral structure but appear as disconnected, almost ghostly segments, as if a piece of a spiral arm has somehow become detached or is only partially formed. One particularly intriguing example has been dubbed the phantom spiral arm, a faint, disjointed arc that seems to extend into the galaxy's outer regions, its very existence a puzzle. It's like seeing a fragment of a spiderweb floating free in the air, not clearly connected to the main web structure. This phantom arm is much fainter than the main spiral arms, and its unusual morphology, its broken, incomplete appearance makes it stand out as an anomaly. Its presence raises fundamental questions about how spiral arms form and persist, and whether this is a temporary feature or a remnant of a more ancient structure. One leading interpretation for the phantom spiral arm connects it to the powerful tidal forces exerted by the Whirlpool's companion galaxy, NGC 5195. We've already seen how this gravitational dance is distorting the main spiral arms and pulling out material to form the tidal bridge. It's plausible that in the past, during an earlier, perhaps closer, pass of the companion galaxy, tidal forces were even stronger in certain regions of the Whirlpool's outer disk. These forces could have ripped out or significantly perturbed a segment of a spiral arm, pulling it away from the main galactic structure. Imagine taking a spiral toy and pulling one of its plastic coils outwards. It might stretch and become distorted, or even break off as a separate piece. Similarly, the tidal forces could have torn a segment of a spiral arm from the Whirlpool's disk, leaving it adrift as a faint, disjointed feature in the galaxy's outskirts. The stars and gas in this tidal remnant would continue to orbit the Whirlpool, but their connection to the main spiral pattern would be severed, creating the appearance of a phantom arm. Studying the stellar population within this phantom arm, its age and chemical composition, could provide clues about its origin. If it contains older stars similar to those in the outer disk, it would support the idea that it was pulled from the Whirlpool itself. Another fascinating explanation for the phantom spiral arm involves the complex phenomenon of density waves. Spiral arms in galaxies are often thought to be the result of spiral density waves, regions of slightly higher density that propagate through the galactic disk like traffic jams on a highway. As stars and gas clouds orbit the galactic center, they slow down as they enter a density wave, pile up temporarily, and then speed up again as they exit. This clustering of material creates the appearance of spiral arms, even though the individual stars and gas clouds are constantly moving in and out of these regions. The ongoing interaction with NGC 5195 is almost certainly influencing the density waves in the Whirlpool Galaxy, perturbing their shape and propagation. The phantom arm could be a transient feature created by a particularly strong or unusual density wave pattern, perhaps a temporary ripple or a resonance amplified by the gravitational pull of the companion. It might be a part of a density wave that has become detached or is propagating in an unusual way due to the chaotic gravitational environment. In this scenario, the phantom arm wouldn't be a collection of material pulled out of the galaxy, but rather a temporary pattern of slightly higher density of stars and gas that, from our perspective, looks like a disjointed arm segment. It would be less about the physical removal of material and more about the shifting patterns of stellar and gaseous distribution driven by the interaction-perturbed density waves. Distinguishing between a tidal remnant and a transient density wave feature is challenging and often requires detailed simulations of the galaxy's dynamics and observations of the motion of stars and gas within the phantom arm. If the stars and gas in the phantom arm are moving in a way that is clearly inconsistent with the overall rotation of the Whirlpool's disk and appears to be following a trajectory that leads outwards from the galaxy, it would strongly support the tidal remnant hypothesis. If, however, the motion is more consistent with material passing through a density enhancement, it might lean towards the transient density wave explanation. The distinct, disjointed nature of the phantom arm also provides a clue. Tidal stripping often creates long, continuous streams of material, while density waves tend to create more coherent spiral patterns, although they can be distorted. The broken appearance of the phantom arm might suggest it's a fragment, which could be consistent with being ripped out by tidal forces or perhaps a section of a density wave that has been disrupted. The phantom spiral arm in the Whirlpool Galaxy is a subtle but significant anomaly, hinting at the complex interplay of forces that shape galactic structure. It's a reminder that galaxies are not static, perfectly formed objects, but are constantly being influenced and reshaped by their cosmic environment, sometimes leaving behind ephemeral or fragmented features that challenge our attempts to neatly categorize their structures and understand their dynamic evolution. As we conclude our journey through the myriad of strange phenomena in the Whirlpool Galaxy, we arrive at a particularly ethereal mystery, one that speaks to us not in light, but in sound, or rather, the electromagnetic equivalent of sound, low-frequency radio waves that astronomers have poetically described as the galaxy's own singing plasma waves. These aren't audible sounds in the traditional sense. Space is a vacuum, so sound waves as we know them can't travel through it. Instead, these are vibrations and oscillations of charged particles within the galaxy's vast plasma, the superheated, ionized gas that permeates interstellar space, which generate electromagnetic waves at very low radio frequencies. When detected by radio telescopes and converted into audible sound waves, these subtle fluctuations can sometimes resemble eerie, low-pitched notes or humming sounds, giving the impression that the galaxy itself is singing. Their detection in the Whirlpool adds another layer to its dynamic portrait, indicating the presence of large-scale processes that are causing the galaxy's plasma to vibrate and ripple on immense scales. What could be orchestrating this cosmic symphony? One prominent source for generating these low-frequency plasma waves is the complex network of magnetic fields that weave through the Whirlpool Galaxy. We've already discussed how these magnetic fields are shaped by gas flows and energetic events like supernova. Now consider how these fields can store and transmit energy through vibrations. Imagine plucking a string on a guitar. It vibrates and produces a sound. In a similar, albeit vastly more complex, way, disturbances in the galaxy's magnetic fields can cause the charged particles tied to these fields to oscillate, generating waves that propagate through the plasma. The ongoing gravitational interaction with the companion galaxy is likely a major driver of these magnetic field vibrations. As the two galaxies tug and pull on each other, they distort each other's magnetic fields, creating stresses and tensions that can lead to oscillations. These vibrations can then travel outwards through the galactic plasma, manifesting as the detected low-frequency radio waves. The specific notes or frequencies of these waves would depend on the strength and geometry of the magnetic fields, as well as the density and temperature of the plasma, much like the pitch of a guitar string depends on its tension, length, and thickness. By studying the characteristics of these singing plasma waves, astronomers can gain insights into the properties of the whirlpool's magnetic fields and the turbulence of its interstellar medium, information that is difficult to obtain through other means. They are like seismic waves traveling through the galaxy's magnetic and plasma structure. Another fascinating possibility is that some of these low-frequency oscillations are being driven by processes occurring very close to the supermassive black hole at the galaxy's center. The turbulent flow of gas in the accretion disk around the black hole and the powerful jets it launches can create instabilities and vibrations in the surrounding plasma. Imagine the chaotic churning near a drain, creating ripples that spread outwards. The immense gravitational forces and the sheer energy output from the black hole can stir up the plasma in the galactic core, generating waves that propagate throughout the galaxy. The peculiar flickering behavior of the nucleus we discussed earlier is evidence of the dynamic and sometimes erratic nature of the accretion process, and these fluctuations could be sending ripples outwards into the surrounding plasma, creating detectable low-frequency waves. Furthermore, if the twin nuclei are indeed two supermassive black holes orbiting each other, their gravitational dance would create powerful disturbances in the surrounding spacetime and plasma, generating low-frequency gravitational waves, though these are different from the electromagnetic waves we're discussing but also potentially exciting plasma waves in their vicinity. While detecting plasma waves directly attributable to binary black hole oscillations from this distance is challenging, the chaotic environment they create could contribute to the overall spectrum of plasma vibrations in the galactic core. The interaction of the black hole's jet with the surrounding interstellar medium could also be a source of these waves. As the jet plows through the gas, it creates shock waves and turbulence which can excite plasma waves. The unusual tilted angle of the whirlpool's jet might even be influencing the way it interacts with the surrounding plasma, creating specific patterns of waves that are different from those generated by a straight jet. By analyzing the frequencies and amplitudes of the detected radio waves, astronomers can try to pinpoint their origin and distinguish between waves generated by magnetic field vibrations, turbulence in the accretion disk, or interactions with the jet. It's a complex puzzle where multiple processes could be contributing to the overall song of the Whirlpool Galaxy. The existence of these low-frequency plasma waves, these cosmic notes, in the Whirlpool Galaxy is a powerful reminder that galaxies are not just collections of stars and gas. They are filled with dynamic plasma and intricate magnetic fields, and these components are constantly interacting and influencing each other on vast scales. The singing plasma waves provide a unique, albeit indirect, way to listen in on the invisible processes that are shaping the whirlpool, offering clues about the turbulence of its interstellar medium, the strength of its magnetic fields, and potentially even the chaotic activity occurring in its very core. They are a subtle but profound aspect of the galaxy's strangeness, revealing a hidden symphony of vibrations that add another dimension to our understanding of this fascinating cosmic system. The vast collection of strange phenomena we've explored in the Whirlpool Galaxy, from its warped structure to its mysterious X-ray halo and synchronized star formation, aren't just random oddities. They are, in large part, direct consequences of a single dramatic event: its ongoing collision and merger with the smaller companion galaxy, NGC 5195. Think of the Whirlpool and its companion not just as two galaxies in the same cosmic neighborhood, but as heavyweight contenders in a slow-motion, gravitational rumble that has been unfolding over hundreds of millions of years and is still actively reshaping both galaxies. Almost every peculiar feature we've discussed can be traced back to the powerful tidal forces, shock waves, and gas flows unleashed by this cosmic interaction. It's the key that unlocks many of the Whirlpool's mysteries. For decades, astronomers have used computer simulations, crunching immense datasets and applying the fundamental laws of gravity and gas dynamics to try and reconstruct the timeline of this galactic dance. These simulations act like cosmic time machines, allowing us to wind back and forward the clock to see how the two galaxies have influenced each other over eons. By comparing the results of these simulations with the detailed images captured by telescopes like the Hubble Space Telescope, which provides us with incredibly sharp views of the galaxy's structures and star populations, astronomers can piece together a compelling narrative of the collision's history. Hubble's ability to resolve fine details in the spiral arms, dust lanes, and stellar populations is absolutely essential in validating these simulated scenarios, providing the observational evidence needed to confirm the chaotic timeline. The picture that emerges from these simulations and observations is one of a grand, sweeping encounter that began perhaps 500 million years ago. Imagine NGC 5195, the smaller galaxy, making its first significant pass close to the Whirlpool. As it swung by, its gravity would have begun to tug on the outer regions of the larger galaxy, initiating the first stages of distortion. This initial encounter wouldn't have been a head-on crash, but more of a glancing blow, a close flyby that nonetheless set in motion powerful tidal forces. Think of two ships passing close to each other in the ocean. The wake from one ship affects the water around the other. On a galactic scale, these tidal forces are immense, acting like cosmic hands pulling and stretching the galaxies out of shape. This first pass likely pulled out some of the initial streams of gas and stars, perhaps laying the groundwork for some of the outer features we see today, or even contributing to the initial stages of forming the tidal bridge. The simulations suggest that the galaxies then moved apart, but their gravitational bond was sealed, and they remained gravitationally bound, setting the stage for future interactions. The most recent and visually dramatic encounter, the one that is currently shaping the Whirlpool into the iconic image we recognize, happened perhaps around 100 to 200 million years ago. This was likely a closer pass, with NGC 5195 plunging through or very near the outer edge of the Whirlpool's disk. This second, closer interaction would have intensified the tidal forces, leading to the pronounced warping of the Whirlpool's spiral arms and the clear formation of the prominent tidal bridge connecting the two galaxies. It was during this pass that vast amounts of gas and dust were likely pulled out, compressed, and channeled towards the Whirlpool's center, fueling the enhanced star formation we observe today throughout the galaxy, particularly in the distorted spiral arms and within the tidal bridge itself. The shock waves generated by this close encounter would have propagated through both galaxies, triggering those synchronized bursts of star formation in mirroring regions. The compression of gas in the Whirlpool's core could have contributed to the overcrowded central star cluster, and the influx of material towards the center could have temporarily increased the activity of the supermassive black hole, perhaps contributing to those ancient radio bubbles from past outbursts. Hubble's detailed images capture the intricate results of this recent major pass, showing the telltale signs of gravitational stress and the resulting bursts of stellar creation. Simulations continue to run, predicting the future of this cosmic pair. It's likely that NGC 5195 will continue to orbit the Whirlpool, making more passes in the coming hundreds of millions of years. With each pass, more material will be exchanged, the galaxies will be further distorted, and star formation will likely continue to be triggered in episodic bursts. Eventually, over billions of years, the smaller galaxy will likely be completely consumed and assimilated into the larger Whirlpool, its stars and gas becoming part of the larger structure. The misaligned gas disk we observe could be gas that was stripped during an even older interaction, or is in the process of settling after this most recent pass. The potential deficit of dark matter might be a consequence of repeated tidal stripping of the outer halo during each close encounter. The singing plasma waves are likely continuous indicators of the turbulence generated by this ongoing gravitational dance. The Whirlpool Galaxy is not just a static visual masterpiece, it's a dynamic system in the middle of a transformative collision, and its strange phenomena are the direct fingerprints of this powerful cosmic event. By studying the whirlpool and comparing it to simulations of galactic mergers, astronomers gain crucial insights into how galaxies evolve, grow, and change shape throughout the universe. It's a front-row seat to one of the fundamental processes that build the large-scale structure of the cosmos, a living, breathing example of galactic cannibalism in action. Even with centuries of observation and our most powerful telescopes trained on the Whirlpool Galaxy, many of the strange phenomena we've explored remain profound, unsolved mysteries, cosmic puzzles that challenge our current understanding of physics and the universe itself. Despite the clear evidence of galactic interaction shaping much of M51, some anomalies defy simple explanation, hinting at deeper, perhaps more exotic processes at play. These are the frontiers of astronomical research, the places where our knowledge reaches its limits and we are forced to confront the unknown, prompting theories that venture into the realms of cutting-edge physics and even speculation about forces and dimensions yet undiscovered. At the very top of this list of baffling enigmas is the persistent question of the whirlpool's missing dark matter. While tidal stripping from the companion galaxy offers a plausible explanation for some reduction in dark matter, the observations seem to suggest an even greater deficit than simulations of interaction alone can easily account for. If the precise measurements of the galaxy's rotation and mass distribution hold up, and if tidal stripping isn't the complete answer, then we're left facing uncomfortable questions about the nature of dark matter itself. Could it be less abundant in some regions of the universe than our prevailing cosmological models suggest? Could dark matter particles interact with each other in ways that cause it to be expelled from galaxies during mergers, a process we haven't fully accounted for? Or are our assumptions about how dark matter is distributed flawed? The whirlpool's apparent lack of dark matter, if confirmed, could necessitate significant revisions to the standard model of cosmology, a fundamental shift in how we understand the invisible scaffolding that holds the universe together. It's a potential crack in our cosmic understanding, and the Whirlpool Galaxy might be where we first glimpse what lies beyond. Adding to the list of the truly perplexing is the enigma of the gamma-ray hotspot, that localized source of high-energy radiation with no clear, obvious culprit. While concentrations of pulsars or enhanced cosmic ray acceleration in a turbulent environment are possible explanations tied to conventional astrophysics, the possibility, however speculative, that this could be related to dark matter annihilation remains a fascinating, albeit unproven, idea. If dark matter particles collide and destroy each other, they could produce gamma rays with a very specific energy signature. Detecting such a signature from the Whirlpool's hotspot would be a monumental discovery, providing direct evidence for what dark matter is and how it behaves at a fundamental level. Alternatively, could this hotspot be related to something even more exotic, perhaps a unique type of high-energy source that we haven't yet catalogued? Could it be a sign of ultra-high-energy particle acceleration in a region far from the central black hole, driven by processes related to the galactic interaction that are beyond our current theoretical models? The mystery of the gamma-ray hotspot forces us to consider the limits of our understanding of particle acceleration and high-energy phenomena in galaxies, pushing us to explore possibilities that lie beyond the conventional explanations of supernova and black hole activity. Then there are the subtle yet deeply puzzling phenomena that hint at processes operating on microscopic or even quantum scales, amplified to galactic proportions. Could some of the inexplicable flickering in the galaxy's core, beyond what can be explained by simple clump accretion or disk instabilities, be hinting at quantum effects near the event horizon of the supermassive black hole, where the rules of gravity and quantum mechanics meet? This is highly speculative territory, but in the extreme environment around a black hole, where space-time is warped to an incredible degree and densities are immense, the conditions might be ripe for quantum phenomena to have observable effects on larger scales. Could the intricate structure of the magnetic fields, with their strange twists and turns, be influenced by quantum processes occurring in the turbulent plasma, acting as a sort of macroscopic manifestation of microscopic chaos? It's a fascinating thought, bridging the gap between the incredibly small and the incredibly large, suggesting that the universe's fundamental rules might be playing out in unexpected ways even in the most distant galaxies. And what about the possibility that some of these anomalies are signs of unseen dimensions or forces that we haven't yet detected? While firmly in the realm of theoretical physics and speculation, the universe has surprised us before. Could the peculiar orientation of the black hole's jet, or the strange distribution of gas and stars, be subtly influenced by gravitational effects bleeding in from extra dimensions? Could dark matter itself be a manifestation of particles or forces operating in these hypothesized dimensions? These are questions that push the boundaries of our current scientific framework, venturing into realms that are difficult, if not impossible, to test with our current technology. But the very existence of these unsolved mysteries in the Whirlpool Galaxy, these phenomena that don't fit neatly into our established boxes, is what drives scientific progress. They are invitations to explore, to question, and to develop new instruments and theories that can take us closer to the truth. What do you think is the most baffling mystery in the Whirlpool Galaxy? Could the missing dark matter be a sign of something fundamentally wrong with our models? Do you believe the gamma-ray hotspot could be related to dark matter annihilation or something else entirely? Share your thoughts and speculations in the comments below. The universe is full of wonders, and the Whirlpool Galaxy, with its many strange phenomena, is a powerful reminder of how much we still have to learn. It's a cosmic canvas painted with the brushstrokes of gravity, light, and mystery, inviting us to continue our exploration of the cosmos and the strange, beautiful things it contains. As we wrap up our deep dive into the strange and captivating Whirlpool Galaxy, it's clear that M51 is far more than just a beautiful spiral in the night sky. It's a cosmic laboratory, a dynamic system where galaxies collide, stars are born and die in dramatic fashion, and gravity plays out its powerful drama on an immense scale. We've explored its bizarre tilted black hole jet, the mysterious X-ray halo, the red and UV anomalies in its arms, the surprisingly low number of ancient star clusters, and the ghostly, singing plasma waves. Each of these phenomena, and the many others we've touched upon, challenges our assumptions and pushes the boundaries of our understanding of how galaxies form, evolve, and interact throughout the universe. The Whirlpool Galaxy, in its unique state of interaction, serves as a living textbook, showing us processes that are fundamental to galactic evolution but are often harder to study in isolated systems. It provides concrete examples of how tidal forces reshape galactic structure, how collisions trigger bursts of star formation, and how supermassive black holes influence their surroundings. Understanding the Whirlpool's intricacies helps us build more accurate models of galaxy formation and better interpret observations of galaxies billions of light-years away, giving us insights into the universe's history and its ultimate fate. The Whirlpool reminds us that the cosmos is a place of constant change, shaped by powerful forces that are still revealing their full effects. But the story of the Whirlpool Galaxy is far from over. As our technology advances, so too does our ability to probe its secrets with unprecedented detail. New generations of telescopes, like the James Webb Space Telescope, are providing astronomers with entirely new perspectives on M51 and galaxies like it. Webb's ability to observe the universe in infrared light with incredible sensitivity and spatial resolution is particularly powerful for studying dusty environments like the Whirlpool's core and its spiral arms. Its infrared eyes can peer through the thick veils of dust that obscure our view in visible light, revealing hidden stars, gas, and even perhaps the nature of that potentially obscured, quiet nucleus and the possible presence of those elusive twin black holes with greater clarity than ever before. Webb can also analyze the chemical composition and temperature of gas and dust with exquisite precision, allowing astronomers to distinguish between different star formation triggering mechanisms, trace the flow of material in the tidal bridge, and better understand the properties of the misaligned gas disk. Future observations with the Square Kilometre Array, a massive radio telescope project currently under construction, will provide even more detailed maps of the Whirlpool's magnetic fields and the distribution and motion of cool gas, potentially unraveling the mysteries of the singing plasma waves and the detached hydrogen cloud with unprecedented clarity. Each new instrument, each new observation campaign, adds another piece to the cosmic puzzle, slowly but surely bringing us closer to a complete picture of this fascinating galaxy. What we've explored today is just a glimpse of the wonders and mysteries contained within the Whirlpool Galaxy. It's a system that continues to surprise and inspire astronomers, reminding us that even in well-studied corners of the universe, there are always new discoveries waiting to be made. Each strange phenomenon we uncover in M51 not only teaches us about that specific galaxy, but also broadens our understanding of the universe as a whole, challenging our theories and pushing the boundaries of scientific knowledge. It's a testament to the incredible power of gravity, the dynamic nature of galactic environments, and the vastness of the unknown that still awaits our exploration. The Whirlpool Galaxy stands as a beacon of cosmic mystery, inviting us to keep looking, keep questioning, and keep pushing the limits of our ability to understand the incredible universe we inhabit. If you're as captivated by the strange phenomena in the Whirlpool Galaxy as we are, and you want to continue exploring the most baffling mysteries of the cosmos with us, make sure to subscribe to our channel and turn on notifications so you don't miss our future journeys into the depths of space. We've got many more cosmic enigmas to unravel, from the perplexing behavior of distant black holes to the search for life beyond Earth. Join our community of fellow space enthusiasts as we continue to marvel at the universe's strange, wonderful, and often